Today, I want to tell you a story that starts with something very small and very ordinary. A simple daydream. Einstein imagines a man falling off a roof. That's it. No equations, no blackboard, just a thought. But if you follow that thought carefully and you refuse to let go when it starts to get strange, something amazing happens. That one idea leads you to black holes, to time slowing down, and to space itself bending. You discover the world isn't flat. It isn't neat. And it isn't very well behaved yet. It's curved. It's weird. And it plays by rules that almost seem to enjoy surprising us. And by the end of this story, you'll see why this strange little daydream became one of the most beautiful ideas we've ever had. I want to tell you a story today about a disaster, quiet disaster, a disaster that happened entirely inside the mind of one man while he was sitting at a desk in a patent office in Switzerland. You see, at the turn of the century, around 1900, physicists were feeling pretty good about themselves. We thought we had it all figured out. We thought we had the owner's manual for the universe. We had the laws of heat. We had the laws of electricity. And most importantly, we had the laws of motion. And the man who wrote that manual, the giant upon whose shoulders we were all standing, was Isaac Newton. Newton was marvelous. He was probably the smartest man who ever lived. He looked at the moon going around the earth, and he looked at an apple falling from a tree, and he had the imagination to realize they are the same thing. He gave us a law, a beautiful, simple rule. You probably learned it in high school. Force equals G times the mass of one thing times the mass of the other thing divided by the distance squared. And it worked. It was perfect. With this one little equation, we could predict where Jupiter would be in 100 years. We could predict the tides rising and falling. It was a clockwork universe. Everything ticked along exactly as Newton said it would. But there was a ghost in the machine. There was a tiny, nagging problem that Newton himself knew about, but nobody else wanted to talk about. And the problem is this. How does the Earth know the sun is there? Look at the solar system. Here's the sun, burning, huge, a giant ball of gas. And here's the Earth, 93 million miles away. And in between them, what is there? Nothing. Vacuum. Silence. Cold. So how does the command to turn get from the sun to the Earth? How does the sun tell the Earth, hey, I'm over here, curve toward me? Does it send a letter? Does it send a radio wave? Does it have a long, invisible rope? Newton didn't know. He assumed, and this is the critical part, he assumed that the connection was instant. He assumed that gravity was like a stiff rod connecting the two. If you wiggle one end, the other end moves immediately. He called it action at a distance. And to be honest, he hated it. He wrote letters to his friends saying, this is absurd. How can a body act where it is not? But the math worked, so everybody just shut up and calculated it. But then in 1905, a young man named Albert Einstein came along, and he broke the machine. Einstein had been working on electricity and magnetism, what we call special relativity. And he discovered something fundamental about the structure of reality. He discovered that light has a speed limit, 186,000 miles a second. Now that is fast. It is very fast. It is fast enough to go around the world 7 times in one snap of your finger. But it is not infinite. It takes time for light to travel. It takes about 8 minutes for light to get from the sun to the earth. And Einstein said something even bolder. He said, nothing in the universe can travel faster than light. No object, no signal, no information, no telepathy, nothing. The speed of light is not just the speed of a photon, it is the speed limit of cause and effect. You cannot affect anything else in the universe faster than the time it takes light to get there. Now put these two things together. Newton says gravity is instant. Einstein says nothing is instant. We have a catastrophe. Let me give you a thought experiment. This is the experiment that kept Einstein awake at night. I want you to imagine a magician, a cosmic magician. And this magician snaps his fingers and poof, the sun vanishes. Gone. It disappeared. No mass, just empty space. Now, according to Isaac Newton, what happens to the Earth? Look at Newton's equation. F equals G times M divided by R squared. Does it have a letter T for time in it? No. It relies only on the mass right now. So if the mass becomes zero, the force becomes zero instantly. So according to Newton, the very instant the sun vanishes, the Earth should fly off in a straight line into the dark. The Earth should know immediately that the sun is gone. But wait, Einstein says nothing. Travels faster than light. Light takes 8 minutes to get here. So if the sun vanishes, we on Earth won't know about it for 8 minutes. We will still see the sun shining in the sky. We will still feel the heat on our faces. We will still see the shadows on the ground. For 8 minutes, the sun is effectively still there for us. The information that the sun is gone has not arrived yet. So look at the contradiction. Are you telling me that the Earth would fly out of orbit while we can still see the sun sitting there? Are you telling me that the gravity message arrived before the light message? That implies that gravity traveled faster than the speed of light. That is impossible. If you can send a signal faster than light, you can break the order of time. You can send a telegram to the past. You can kill your own grandfather before you were born. The whole logic of the universe falls apart. So Einstein realized Newton must be wrong. He wasn't just a little bit wrong about the numbers. He was philosophically wrong about how the world works. The Earth cannot fly off instantly. For 8 minutes, the Earth must continue to orbit around a sun that does not exist. It must orbit a ghost. It must dance around an empty spot in the sky simply because the news hasn't arrived yet. So the question became how? How does the gravity get from there to here? If it can't be a rigid rod, if it can't be instantaneous, what does it mean? It must be something else. It must be a ripple, a wave, a distortion in the environment, something that travels across the empty space, taking its time, obeying the speed limit, carrying the message, hey, the sun is over here. And this realization that gravity is not a magical instant connection, but a physical process that takes time, this forced Einstein to throw away the old rule book. He had to reinvent the entire universe. He had to find a way to explain how a rock can communicate with another rock across empty space without touching it. And to do that, he had to have what he called the happiest thought of his life. So Einstein is stuck. He knows Newton is wrong. He knows that gravity cannot be a magical instant force. It has to be something else. But what? He sits in his chair at the patent office in Bern. It is 1907. He is supposed to be looking at patents for electric motors, but he is staring out the window, and then suddenly it hits him. He has a thought so simple, so beautiful, that he later called it the happiest thought of my life. He imagines a man falling off a roof. Now, don't worry, in Einstein's imagination, there is a big pile of hay at the bottom or a safety net. The man is perfectly safe. But think about the man while he is falling. I want you to really put yourself in his shoes. Imagine the man wakes up and he is falling through the AIR. And imagine he pulls his keys out of his pocket and lets go of them. What happens and what? Do the keys fall to the ground faster than him? No. Galileo taught us that everything falls at the same speed. Heavy things, light things, they all go down together. Do the keys stay up in the air above him? No. To the man, the keys just float right next to his face. If he tries to pour a glass of water, the water comes out of the bottle and forms a floating ball. It doesn't fall down past his knees. And the man himself, does he feel the heavy No, he feels weightless. He feels like an astronaut. If he closes his eyes, he cannot tell that gravity is pulling him. As far as he is concerned, gravity has vanished. By simply giving in to the fall, by surrendering to the pull, he has canceled out gravity perfectly. Einstein realized if a person falls freely, he will not feel his own weight. This is a clue, a massive clue. It suggests that gravity is not some painted-on force that is always attached to you. It is something that can be erased just by moving in the right way. Now, Einstein flips the picture. He says, okay, if falling makes gravity disappear, can I make gravity appear out of nothing? Let's play a game. I want you to imagine you wake up in a box, a painted room, no windows, you cannot see outside. You're floating in the middle of the room. You have no weight. You assume you are in deep space, far away from any stars or planets. Zero gravity. It is silent. It is still. Now suppose I attach a huge hook to the top of your box, and I attach a rope to the hook, and I attach the rope to a rocket ship, and I turn on the engine. The rocket starts to pull the box up. It accelerates faster and faster. Let's say it accelerates at exactly 1 g, 32 feet per second squared, the same rate that things fall on Earth. What happens to you inside the box? Well, the floor of the box rushes up and hits your feet. Wham! Suddenly you are standing on the floor. You feel pressure on the soles of your feet. You feel your legs holding you up. You feel weight. Now you take a ball from your pocket and you drop it. What actually happens? Well, you let go of the ball. The ball is just floating there in space. It has no forces on it, but the floor is accelerating up towards the ball. So the floor smacks into the ball. But to you, inside the box, it looks like the ball fell down and hit the floor. You look at this. You feel the weight in your legs. You see the ball fall. And you say, aha! I must be sitting on the earth. Gravity is pulling me down. But you are wrong. There is no gravity. You are in deep space. You are just accelerating. But here is the kick. Here's the thing that makes your brain hurt. Is there any experiment you can do inside that box to prove you are moving? Can you find a difference between sitting on Earth and accelerating in a rocket? Einstein thought about it. He thought about pendulums. He thought about springs. He thought about dropping weights. And he realized, no, there is no difference. The physics is identical. Nature does not know the difference between gravity and acceleration. If you are pushed into your seat because you hit the gas pedal in your car, or if you are pushed into your seat because you're sitting on the planet Jupiter, it is the same sensation. It is the same physical law. This is called the principle of equivalence. And this was the key that unlocked the universe. Because Einstein said, if I cannot distinguish between gravity and acceleration, then they must be the same thing. Gravity is not a force pulling you. Gravity is indistinguishable from acceleration. And this gave him a way to predict the future. He said, okay, I don't know much about gravity yet. It's mysterious, but I know everything about rockets. Rockets is simple mechanics. So if I want to know what gravity does to a light beam or to a clock, all I have to do is figure out what a rocket does to a light beam or a clock. Whatever happens in the rocket must happen near the Earth because they are the same thing. So Einstein sat down to imagine what happens if I shoot a laser beam across a moving rocket ship. And what he found changed our understanding of reality forever. So we have this crazy idea, the principle of equivalence. We said that sitting in a room on Earth is exactly the same as sitting in a rocket ship that is speeding up. Nature can't tell the difference. You can't tell the difference. If you drop a ball in the rocket, it hits the floor. If you drop a ball on Earth, it hits the floor. It is the same physics. Now Einstein says, if this is true, if this is really a law of nature, then I can use the rocket to find out things about gravity that Newton never dreamed of. Let's do an experiment. We are back in our rocket ship. We are way out in deep space, no stars, no planet, just us and the engine. The engine is pushing us up. We are accelerating, and I have a flashlight, or better yet, a laser, a pointer. And on the side of the rocket, there is a little window, glass. I'm going to shine the laser beam through the window. It is going to shoot across the room horizontally and hit the wall on the other side. Zip across. Now let's look at this from 2 points of view. This is how relativity works. You have to look at it from the outside and then from the inside. First, the outside view. Imagine a man floating in space outside the rocket, watching us through the glass. He sees the laser turn on. A photon. A little bullet of light leaves the flashlight. Now, once light leaves the flashlight, it is free. It has no connection to the ship anymore. It travels in a perfectly straight line. Newton says so. Maxwell says so. Light goes straight. So the man outside sees the bullet of light go perfectly straight across space. Second, the inside view, you are inside the rocket. But remember, the rocket is accelerating up. While that little bullet of light is traveling across the room, what is the room doing? The room is moving up. The floor is coming up to meet the light. So the light enters the window here. But by the time it gets across the room, the wall has moved up. So the light doesn't hit the spot directly across. It hits a spot lower down on the wall. Do you see? The light entered at eye level, but it hit the wall at knee level. I am exaggerating the speed, of course, but the principle is real. Now imagine you are inside. You don't know you're moving. You think you're just standing still in a room. You turn on your laser. You aim it straight across. But you see the beam go down. You see the beam curve towards the floor. It makes a parabola, just like a tossed ball. You would say, my God, the light is falling. Something is pulling the light down. Now here is the punchline. Here is where Einstein earns his pay. He says, if the rocket bends light, and if the rocket is the same as gravity, then gravity must bend light. If you stand on the earth and you shine a laser beam, the gravity of the earth must be pulling that light down toward the floor. Just a tiny bit, but it must be happening. Now stop and think about why this is so disturbing. Think about Isaac Newton again. Newton said gravity is a force that pulls on mass. F equals G times M divided by R squared. M is mass. If you have a rock, gravity pulls it. If you have a feather, gravity pulls it. But a light has no mass. Light is weightless. It is pure energy. If you put a sunbeam on a scale, it weighs 0. If M is 0, the force is 0. Newton says gravity should ignore light. Gravity should try to grab the light, and its hand should go right through it like a ghost. But Einstein's rocket argument says no, the light must bend. So we have a paradox. How can a heavy object like the Earth pull on a weightless object like light? How can you pull something that has no handle? And Einstein realized maybe we are looking at it all wrong. Maybe gravity isn't pulling the light. Maybe gravity is doing something else. Go back to the rocket. Why did the light hit the wall lower? Did the rocket pull the light? No, the light went straight. The rocket itself moved. The geometry of the room changed relative to the light. So Einstein said, maybe that is what gravity is. Maybe the Earth isn't reaching out and grabbing the light beam. Maybe the Earth is changing the shape of the room that the light is traveling through. The light is trying to go straight. It is doing its best. But the space itself, the very fabric that the light is traveling in, is curved. And a straight line on a curved surface ends up looking like a curve. This was the beginning of the end for the idea of force. We had to stop thinking about muscles and ropes and start thinking about geometry. But how do you curve empty space? That sounds ridiculous. Well, let me tell you about the bug, the geometry of the hot plate. So we have reached a very strange point in our detective story. We have decided that gravity is not a force, it is not a rope, it is not a muscle pulling on things. We have decided that gravity is a curvature. The light bends not because the earth pulls it, but because the space the light is traveling through is bent. Now I can see the look on your faces. You are looking at me with great suspicion. You are saying, Professor, this is nonsense. I can see space. It is right here between my nose and my hand. It is empty. It is nothing. How can you bend nothing? You can bend a piece of wire. You can bend a mattress. But how do you bend emptiness? And even if it is bent, we are inside it. We are trapped in the universe. We cannot step outside to look at the ball. So how can we possibly measure the curvature of the room we are standing in? To explain this, I want to invite you to a dinner party. But this is a dinner party for bugs. Imagine a giant flat sheet of metal, a hot plate. And right in the middle of this plate, we light a fire, a very hot fire. So the plate is extremely hot in the center, and it gets cooler and cooler as you go out to the edge. Now we put our bugs on this plate. These are special bugs. They are made of the same metal as the plate, and they have rulers, little measuring sticks made of the same metal. And we have a law of physics, old-fashioned physics. Heat makes things expand. When the ruler gets hot, it expands, it gets longer. When the bug gets hot, he expands. Everything expands together. So the bug doesn't know he is getting bigger. If he looks at his ruler, it looks the same to him because he grew too. Now let's ask the bug to do some geometry. We ask him to verify the laws of Euclid. We ask him to measure a circle. We draw a circle around the fire. We stay far away, near the cool edge. The bug takes his ruler. He walks around the circle. Click, click, click. He counts the rulers. Since it is cool, the ruler is short, so he has to use a lot of rulers to go around. He writes down a big number for the circumference. Now we ask him to measure the radius, the distance from the edge straight into the center. So he starts walking toward the fire. What happens? As he gets closer to the middle, it gets hotter. His ruler expands. It gets huge. But he doesn't know it. He just thinks, boy, I am covering a lot of ground today. Because his ruler is so big, he needs fewer steps to get to the center. He counts 1, 2, 3, and I'm there. He writes down a small number for the radius of. Now he sits down to check his math. Euclid says that the circumference should be equal to 2 times pi times radius. C equals 2 pi/r. But the bug looks at his notebook. His circumference is huge. His radius is tiny. The equation doesn't work. There is too much circumference for such a small radius. There is more room in the middle than there should be. The bug is confused. He says, my math is broken. But we know the truth. We are looking from the outside. We say, no, Mr. Bug, your math isn't broken. Your geometry is broken. You are living in a world where the scale changes from place to place. And this is what Einstein says happens near the sun. The sun is the fire. But it doesn't heat up space. Space doesn't have a temperature. Instead, the mass of the sun changes, the metric. Metric is just a fancy word for the length of the ruler. Gravity distorts the scale of reality. Close to the sun, a meter is not the same as a meter far away. Close to the sun, a second is not the same as a second far away. So when the earth tries to move, it is like the bug. It wants to go straight. It wants to follow the simplest path. But the grid paper that it is walking on is warped. The ruler keeps changing size. And because the grid is warped, the straightest line turns out to be a circle. The Earth thinks it is going in a straight line forever. But because the space around the sun is distorted, like the hot plate, that straight line wraps around it and bites its own tail, it becomes an orbit. So you see, we don't need force. We don't need hooks and rope. We just need a rule that says mass changes the ruler. Mass tells space how to curve, and the objects just follow the bumps and valleys of that curve. But Einstein was not finished. He had this beautiful picture of the hot plate, but he had a problem. Gravity doesn't just stretch space, it stretches time. Remember the rocket ship? If you put a clock on the floor of the rocket and a clock on the ceiling because the rocket is accelerating, the clock on the ceiling is moving slightly faster through space signals than the one on the floor. Einstein realized that gravity must do the same thing. Gravity slows down time. A clock near the sun ticks slower than a clock far away. So it is not just the ruler that changes size, it is the stopwatch that changes speed. And this is why we call it space-time. You cannot separate them. The Earth is curving through a four-dimensional landscape of warped space and warped time. And now Einstein had the idea, but he didn't have the equation. He needed to write a law that would tell you exactly how much the fire stretches the ruler and slows the clock. And that turned out to be the hardest homework assignment in the history of science. It took him 10 years, and it almost killed him. So we have the picture, we have the idea, we have the hot plate, we have the idea that the sun curves the space around it, and the Earth simply follows the curve. It is a beautiful idea, it is elegant, it makes sense philosophically, but in physics, a beautiful idea is useless unless you can calculate with it. You need to be able to predict exactly where the planet will be next Tuesday at 9 o'clock a.m. If you can't give me a number, you don't have a theory, you just have a daydream. And this is where the tragedy begins, or rather the struggle, because Albert Einstein had the happiest thought in 1907, but he did not write down the final equation until 1915. It took him 8 years of wandering in the desert, 8 years of sweat and headache and wrong turns. Why? Why was it so hard? Because the mathematics you need to describe a curved four-dimensional blob of space-time simply did not exist in the books of physics. Newton used algebra, easy, F equals ma. 3 letters, you can teach it to a high school student. But to describe a curved geometry, you need something else. Think about a bed sheet. If you lay a bed sheet flat on a mattress, it is easy to describe. You can just say it is flat, zero curvature. But now crumple it up, throw some pillows under it, twist it. Now try to write an equation that describes every single hill and valley and wrinkle on that sheet. It is a nightmare. The curvature is different here. It is different. There it is twisted. This way it is stretched that way. You cannot describe it with one number. You need a map. You need a grid of numbers. Einstein realized he was not a good enough mathematician to do this. He went to his old college friend, Marcel Grossman. He said, "Grossman, you must help me or I will go crazy." And Grossman said, "Well, there is this obscure branch of mathematics called Riemannian geometry. Nobody uses it for physics. It deals with curved surfaces in multiple dimensions. It used these things called tensors. A tensor is a beast. Newton's law is one equation. Einstein's law using these tensors is actually 10 equations all tangling up together. It is a multi-headed monster. And Einstein had to wrestle with this monster for years. He would write an equation, realize it didn't conserve energy, throw it away. Write another, realize it didn't match reality, throw it away. He was exhausted. His hair turned gray. His stomach gave him trouble. His marriage fell apart. He was fighting the universe all by himself. But then in November of 1915, he felt he was getting close. He found an equation that looked beautiful. It looked robust, but he had to test it. He had to prove it wasn't just another daydream. And nature had given him a gift, a puzzle. The planet Mercury. You see, for 50 years, astronomers had known that Mercury was misbehaving. All the planets orbit the sun in an ellipse, an oval, and usually that oval stays put. But Mercury is close to the sun. It moves fast. And astronomers noticed that the orbit of Mercury was shifting. It was wobbling. Every century, the oval would turn a tiny, tiny bit. It was a shift of 43 arcseconds per century. That is tiny. It is like looking at a penny from 2 miles away. But it was leading. And Newton could not explain it. According to Newton, Mercury should not wobble that much. Astronomers were so desperate that they invented a fake planet. They said, there must be an invisible planet, let's call it Vulcan, hiding inside Mercury's orbit, pulling on it. They looked for Vulcan for years. They never found it because it wasn't there. So Einstein sits down at his desk. It is 1915. He takes his new terrifying equation of general relativity. He puts in the mass of the sun. He puts in the distance of Mercury. He calculates the curvature of space near the sun. And he asks the equation, how much should the orbit wobble? He does the math. It is pages and pages of calculation. He gets to the end. He sums up the number. And he looks at the result. The number on the paper is 43. 43 arcseconds. Exactly. Precisely. To the decimal point. Can you imagine that feeling? He is alone in his room. He hasn't looked through a telescope. He has just been scribbling symbols on a piece of paper. And those symbols reached out across millions of miles of space and described the motion of a planet perfectly. A motion that had baffled the greatest minds for half a century. Einstein later said that when he saw that number, he had heart palpitations. He felt like something snapped inside him. He was so excited he couldn't work for days because he knew at that moment he didn't need to ask anyone else. He didn't need a Nobel Prize. He knew that he had heard the whisper of God. He knew that gravity was not a force. He knew that space and time were curved, and Mercury was just following the twisted path of the valley near the sun. Newton was overturned. The mystery of Vulcan was solved. But Einstein wasn't done. Mercury was just explaining something we already saw. To really win, to really prove he was right, he had to predict something that nobody had ever seen before. He had to bet the farm on a prediction that seemed impossible. He had to bet on the eclipse. So Einstein has Mercury. He has the numbers. He knows he is right. But in science, you have to be careful. It is not enough to explain the past. Anyone can fit a curve to old data if they wiggle the numbers enough, and that is cheating. To really win, to really prove you know the secrets of the universe, you have to predict the future. You have to bet your reputation on something that nobody has ever seen before. You have to put your head on the chopping block and say, if I am wrong about this, my whole theory is trash. So Einstein looks at his equation and he says, light. Remember the rocket ship? We said that gravity must bend light. Well, the sun is a very heavy object. It creates a deep valley in space. So if a star is shining behind the sun and its light passes right next to the edge of the sun on its way to Earth, that light should fall into the valley and curve. Now here is the drama. If you use Newton's theory and you squint and you pretend light has a little bit of mass, Newton predicts a tiny bend, a shallow curve. But Einstein's theory, because it curves both space and time, predicts to double the bending. So we have a contest, a heavyweight fight. In this corner, Isaac Newton. He says the star moves a tiny bit. In this corner, Albert Einstein. He says the star moves a lot. Nature has to decide. There is no arguing. We just have to look. But there is a practical problem, a big one, Nasir. To seize this bending, you need to look at a star that is sitting right next to the sun in the sky. But if you look at the sun, you go blind. The sky is blue. The sun is blazing. You cannot see stars in the daytime. So how do we perform the experiment? We have to wait for nature to help us. We have to wait for a total solar eclipse. We need the moon to slide in front of the sun, block out the fire, turn day into night, and let us see the faint little stars right next to the rim of the sun. In 1919, a British astronomer named Arthur Eddington decided to settle the bet. Now, I want you to think about the context here. The world had just finished fighting World War I. England and Germany were enemies. They had been killing each other in the trenches for years. And here is a British scientist, Eddington, traveling to the coast of Africa to test the theory of a German scientist, Einstein. It is a marvelous moment. It shows that science transcends borders. Science doesn't care about your nationality. It only cares about the truth. So Eddington goes to the jungle, to the island of Principe, and it is a disaster. It rains all day. Clouds everywhere. He is terrified. He has traveled thousands of miles, carrying these heavy telescopes, and he might see nothing. But at the last moment, the clouds part. The moon covers the sun. The sky goes dark. The stars pop out. He takes the pictures. Click, click, click. He brings the photographic plates back to England. Now, what is he looking for? He takes a picture of the stars without the sun. That is the true position. Then he puts the eclipse photo on top. If Einstein is right, the stars near the sun should look like they have been pushed away. Because the light curved around the sun to get to us, our eye traces it back in a straight line, and we see the star in the wrong place. Eddington measures, he gets out his ruler, he compares the dots, and the result comes in. The stars had shifted, and they didn't shift by the Newton amount. They shifted by the Einstein amount. The light was bent, space was curved. When the news came out, it was absolute pandemonium. The headlines the next day were huge. The New York Times wrote, "Light all askew in the heavens, Einstein theory triumphed." Overnight, literally overnight, Albert Einstein went from being a quiet professor to being the most famous man on earth. He became an icon. You know, the hair, the face that started here. Not because he invented a gadget, not because he built a bomb, but because he changed our fundamental understanding of where we live. He showed us that the space we live in is not a fixed wooden stage. He showed us that the universe is flexible. It is like a fabric that ripples and bends and twists. He showed us that the thing we call gravity is just the shape of that fabric. It was the death of the old physics and the birth of the new. And you know what Einstein said when they sent him the telegram, when they told him you were right? He didn't jump up and down. He didn't scream. He just smiled and said, "I knew it was right. The theory is too beautiful to be wrong." And there is always a but. Once you accept that space can curve you, open the door to some very scary things. Because if the sun curves space a little bit, what happens if you have something heavier? What happens if you curve space so much that it rips? Let's talk about the black holes. So we have opened the door. We have proven that space is flexible. We have proven that mass curves geometry. And everybody is happy. We have a new theory of gravity, and it works perfectly for the planets and the stars. But in physics, you have to be very careful when you write down a new law, because sometimes the mathematics is smarter than you are. Sometimes the equations tell you things that you didn't intend to say, things that seem crazy. Right after Einstein published his theory, a man named Carl Schwarzschild took a look at it, and he asked a very dangerous question. He said, "Okay, Einstein, you told us that the sun curves space like a gentle valley, and that is fine. But what happens if I take the sun and I squash it? Imagine we have a trash compactor, a cosmic trash compactor, and we take the sun, all that mass, all those millions of tons, and we squeeze it. We squeeze it down until it is half its size. Then we squeeze it again. We keep squeezing until the sun is only 3 miles wide, the size of a small town. Now the mass is the same. It is still the sun. But the density is monstrous. And the curvature, the valley in space is no longer a gentle slope. It has become a bottomless pit. The sides of the valley are vertical. Now think about the rule we learned earlier. The speed of light is the limit. To escape the Earth, a rocket has to go 25,000 miles per hour. That is the escape velocity. If you make the Earth heavier, you have to go faster to get out. But if you crush the sun down to 3 miles wide, the gravity becomes so strong, the valley becomes so steep, that the escape velocity becomes greater than the speed of light. Now put 2 and 2 together. Nothing can go faster than light. You need to go faster than light to get out. Conclusion, nothing gets out. Not a rocket, not a particle, not even light itself. If you shine a flashlight up from inside this hole, the beam of light tries to climb up. It slows down in energy, and it falls back in. It is a trap, a one-way door in the universe. You can check in, but you can never leave. From the outside, it would look like a spot of pure darkness, a hole in the fabric of reality. We call it a black hole. Now, you have to understand, when Einstein saw this, he hated it. He absolutely hated it. He said, "This is just mathematics. This is a quirk of the numbers. Nature would never allow such an abomination to exist." He thought there must be some law that prevents a star from being crushed that small. He spent years arguing that black holes were impossible. But nature doesn't care what we think is impossible. Nature follows the laws. And the law says, if you put enough mass in a small enough box, you break the floor. You rip the space-time. And now we know they are real. We see them. There is a monster sitting right in the center of our own galaxy, weighing 4 million times as much as the sun, eating stars for breakfast. The math was right. Einstein was wrong to doubt it. But that wasn't the only monster hiding in the equation. There was an even bigger one, the biggest one of all. Einstein decided to take his equation and apply it to the whole universe. He wanted to build a model of the entire cosmos. And he found something very disturbing. His equation told him that the universe cannot stand still. Think about it. Gravity is a pull. It attracts. If you have a universe full of galaxies and they are all pulling on each other, the universe should be collapsing. It should be shrinking like a balloon losing air. Or if it had a big kick at the start, it should be expanding. But it cannot just sit there, static and unchanging. Gravity won't let it. But Einstein, he was a man of his time. He believed in the fixed universe. He thought the universe was eternal. It had always been there. It would always be there. So he cheated. He actually went into his beautiful equation and he added a fudge factor. He added a term called the cosmological constant. It was a made-up pushing force to counteract gravity and hold the universe still. He forced the math to match his prejudice. And then a few years later, a man named Edwin Hubble looked through a telescope. And what did he see? He saw the galaxies rushing away from us. He saw that the universe is expanding. It is getting bigger every day. If Einstein had just trusted his own equation, he would have predicted the expansion of the universe before anyone saw it. He would have predicted the Big Bang. Because if the universe is getting bigger today, that means yesterday it was smaller. And 1 billion years ago, it was tiny. And 13.8 billion years ago, it was all at one point. Einstein called that fudge factor the biggest blunder of my life. But I don't think it was a blunder. I think it shows us something important. It shows us that even the greatest genius is human. And it shows us that the laws of physics are not just inventions of our mind. They are real. They are out there. And if you listen to them, really listen to them, they will tell you the history of the universe. So we have gone from a falling elevator to the birth of the cosmos. That is the power of an idea. So where does this leave us? We have come a long way in the last hour and a half. I want you to stop and look at the path we took, because the path, the road itself, is just as important as the destination. Remember where we started? We didn't start with complex equations. We didn't start with computers. We didn't start with telescopes looking at the edge of the universe. We started with a daydream. We started with a man falling off a roof. We started with a man in a box floating in deep space. Cool. It was a tiny, simple idea, the idea that falling and floating are the same thing, the idea that gravity can be erased if you just let go. It is an idea that a child could understand. And yet when Einstein took that little seed and planted it, look what grew out of it. He watered it with logic. He fed it with mathematics. And it grew into a tree that covers the entire universe. It grew into the bending of light. It grew into the slowing of time. It grew into the expanding universe and the Big Bang. It grew into the monsters in the dark, the black holes, all of that complexity, all of that magnificence was hidden inside that one simple thought. And that, to me, is the beauty of physical law. It is not that the universe is complicated. It is that the universe is built on a few deep, simple principles that play out in infinite variations. You know, people often ask me, Professor, doesn't science remove the beauty of the world? Doesn't explaining the rainbow make it less magical? And I say, no, it adds to the beauty. To know that the rainbow is made of light, obeying the laws of reflection and refraction, to know that the sensation of weight on your feet is actually the curvature of time, that makes it more marvelous, not less. And there is a lesson here, a lesson for all of us. The lesson is that nature is far more imaginative than we are. If I sat in a room by myself and tried to invent a universe, I would never have come up with curved space-time. It is too crazy. I would have made it simple. I would have made it flat. But nature, she has a better imagination. She dreams up things that we could never guess. And our job as scientists, as human beings, is not to tell nature how she should behave. Our job is to listen, to look, to be surprised. We are just the audience, watching the greatest show in existence. I am still amazed, and I think I will always be amazed, that such a simple idea, the equivalence of falling and floating, could lead to such a magnificent structure. It turns out that the man falling off the roof wasn't falling down. He was falling into a new understanding of who we are and where we live. It is a wonderful world, and I am glad we figured out a little bit of how it works. Thank you. We are going to talk about a mistake, but not just any mistake. We are going to talk about a mistake made by the most famous mind of the 20th century, Albert Einstein, and how that mistake, which he tried to throw into the wastebasket of history, turned out to be the most important, most mysterious, and the most dominant thing in the entire universe. It is a story about how we try to force nature to behave the way we think it should, how nature politely ignores us, and how, if we are lucky, our errors contain more truth than our triumphs. To really understand this, we have to start by clearing our minds of what we think we know. We have to go back to the state of physics before anyone had any idea that the universe was growing or changing or doing much of anything at all. Imagine you are sitting at a desk in Berlin. The year is 1915 or 1916. You are Albert Einstein. You have just spent 10 years of your life, 10 years of intense agonizing, beautiful mental labor trying to figure out how gravity works. Now, up until that point, we had Isaac Newton's picture, and Newton's picture was pretty good. He worked for 200 years. It explained why apples fall, why the moon goes around the earth, and why the planets go around the sun. But Newton had a problem, and he knew he had a problem. He didn't know how gravity actually did what it did. He wrote down the formula. He said the force is equal to some constant times the mass of one thing, times the mass of another thing, divided by the square of the distance between them. But if you asked him, how does the sun reach out across millions of miles of empty space and pull on the earth instantly without anything in between, Newton said, I don't know. He called it action at a distance, and he didn't like it. He basically said, the math works. Don't ask me how the plumbing is hooked up. So Einstein comes along and says, let's look at this differently. Let's look at space and time, not as some empty room where things happen. In the old view, space was like a theater stage. You put the actors on the stage, they move around, they do their play, but the stage doesn't care. The stage just sits there. Einstein said, no, that is wrong. Space and time are not the stage. They are the actors. They are dynamic. They are flexible. They can bend, they can stretch, they can ripple. When you put a massive object like the sun into this fabric of space-time, the fabric bends. It's like putting a heavy bowling ball on a trampoline. The trampoline sheet curves down, and then if you roll a little marble across the trampoline, the marble doesn't roll in a straight line anymore. It rolls in a curve around the bowling ball. It's not that the bowling ball is reaching out with some invisible spooky hands and grabbing the marble. It's that the bowling ball has changed the shape of the world the marble is moving through. The marble is just trying to go in a straight line, but the straight line has become a curve because the space itself is curved. That is gravity. It is geometry. It is an incredibly elegant idea. It is beautiful. And the best part is, it worked. It explained things Newton's theory couldn't quite get right. There was this little wobble in the orbit of Mercury. It's called the precession of the perihelion. Newton's equations got close, but they were off by a tiny fraction of a degree every century. It was a tiny thing, but it was there. Einstein's new equations of general relativity calculated it exactly. It predicted that starlight passing near the sun during a solar eclipse would be bent by the curvature of space, and a few years later some astronomers went out and measured it, and they found out he was absolutely right. But then Einstein decided to do something very bold. He decided to apply his brand new equations, which work so beautifully for the solar system, to the entire universe. All of it. All the stars, all the space, everything we could see. Now, when you do that, you have to make some assumption. You can't solve the equations for every single star individually. That's too hard. So you simplify. You say, let's assume that if we step back far enough, the universe looks pretty much the same everywhere. It's like looking at a crowd of people. Up close, you see individual faces. But from an airplane, the crowd just looks like a smooth gray carpet. We call this the cosmological principle. The universe is homogeneous and isotropic. It looks the same in every direction, and it's the same no matter where you are. So Einstein takes this smooth, average universe and puts it into his equations, and he waits to see what the math tells him. And the math tells him something he doesn't want to hear. The math says the universe cannot sit still. Think about it. Gravity is an attractive force. Everything pulls on everything else. If you have a universe filled with matter, stars, dust, gas, whatever, and it's just sitting there, what is it going to do? It's going to fall together. Every piece of matter is going to pull on every other piece. The outer parts will pull inward, the inner parts will pull together, and the whole thing will start to collapse. It's like a giant pile of sand that just slips and falls into a heap. The universe should collapse into a big, hot, messy, gravitational crunch, or if the universe started out flying apart, the gravity should be slowing it down, and eventually it might turn around and collapse anyway. But what the equations absolutely would not allow was for the universe to just sit there, quiet, peaceful and unchanging. Now, this is where the human element comes in. Scientists are supposed to be completely objective. We are supposed to look at the math, look at the data, and say, well, that's what the equations say, so that must be the way it is. But we are people. We have prejudices. We have feelings. We have things we want to be true. And Einstein wanted the universe to be static. Why? Because that's what everyone had believed for thousands of years. When you look up at the night sky, it looks permanent. Sure, the planets move, but they move in regular, predictable cycles. The background stars, the constellations, they stay the same. The Greeks saw the same constellations we see. The ancient Egyptians saw them. The heavens are fixed. It was a deeply ingrained, rock-solid assumption of human culture and science. The universe is eternal, static, and peaceful. So Einstein looked at his beautiful equations, and he looked at his assumption of a static universe, and he realized they didn't match it. He had a choice. He could trust his equations and say, hey, maybe the universe is collapsing or expanding. Or he could find a way to fix the equation, so they gave him the answer he wanted. He chose to fix the equation. He looked at the left-hand side of his equation. On the left side, you have the math that describes the geometry of space-time. On the right side, you have the math that describes the matter and energy. Einstein realized that he could add a little term to the left-hand side without breaking the mathematical consistency of the theory. It was a term that didn't depend on how much matter was in space. It was just a property of space itself. He labeled it with the Greek letter lambda, and he called it the cosmological constant. What did this lambda do? Physically, it acted like a kind of anti-gravity. While normal gravity is attractive, it wants to pull things together. This new term represented a repulsive force that pushed space apart. And the weird thing about it was that it didn't get weaker when things got further apart. Normal gravity gets weaker as distance increases. But this cosmological constant represented a pressure that was uniform throughout the entire universe. It was built into the very fabric of empty space. So Einstein had a plan. He said, if I choose the value of lambda very carefully, just the right number, then the outward push of this cosmological constant will exactly balance the inward pull of gravity. And it's like a tug of war where both sides are pulling with the exact same strength. The rope doesn't move, the universe doesn't expand, and it doesn't collapse. It just sits there, static and eternal, exactly the way he wanted it to be. He was satisfied. He published his paper, and for a little while, he thought he had solved the problem of the cosmos. But there is a catch. There is always a catch when you force your equations to match your prejudices. Even on paper, Einstein's static universe was a house of cards. It was in what we call unstable equilibrium. Think of a pencil balanced perfectly on its tip. If you get it exactly vertical, in theory, it can stay there. The forces are balanced. But what happens if a tiny draft of wind hits it? What happens if there is a tiny vibration in the table? The pencil tilts a little bit, you cut, and the moment it tilts, the forces are no longer balanced. Gravity pulls it down even more, and it falls over. Einstein's static universe was just like that balanced pencil. If the universe expanded by even a tiny fraction, the density of matter would decrease, which means the inward pull of gravity would get a little weaker. But the outward push of the cosmological constant stays the same, because it's a property of space itself, and now there's more space. So the outward push wins. It pushes the universe to expand even more, which makes gravity even weaker, which makes the expansion even faster. The universe flies apart. On the other hand, if the universe contracted by a tiny fraction, the matter would get closer together. Gravity would get stronger. It would overcome the cosmological constant, and the universe would collapse. So even if Einstein could set the balance perfectly, the slightest disturbance, a star moving, a fluctuation in gas, would ruin the balance, and the universe would start either expanding or collapsing anyway. It was a mathematical illusion. It didn't represent a stable, real-world universe. But before anyone could really press him on this mathematical instability, something else happened. The real world got in the way. We have to go from Berlin across the Atlantic Ocean to a mountain in California called Mount Wilson. There was a man there named Edwin Hubble. Hubble was a very interesting character. He was an athlete, a boxer, a soldier, and an astronomer. And he had access to the largest telescope in the world at the time, the 100-inch Hooker telescope. Hubble was interested in these faint, fuzzy patches of light in the sky that astronomers called nebulae. Nobody really knew what they were. Some people thought they were just clouds of gas inside our own galaxy, the Milky Way. Other people had this wild idea that they were island universes, huge, distant collections of stars entirely separate from our own galaxy. To solve this, Hubble had to find a way to measure how far away these things were. That is one of the hardest things to do in astronomy. When you look at a light in the distance, if it looks faint, is it because it's a small, weak light close by, or is it a giant, powerful searchlight really far away? You can't tell just by looking. You need what we call a standard candle. You need some object where you already know how bright it is at the source. If you know how bright it is at the source and you measure how bright it looks to your telescope, you can use the simple law of physics that says light gets dimmer with the square of the distance to figure out exactly how far away it is. Hubble found his standard candles. They were a type of star called Cepheid variable. These are stars that pulse. They get brighter and dimmer in a regular rhythm. And another astronomer, Henrietta Leavitt, had discovered that there is a direct relationship between how fast these stars pulse and how bright they actually are. The slower they pulse, the brighter they are. So Hubble pointed his giant telescope at the Andromeda Nebula. He found a Cepheid variable star. He watched it night after night, measured the timing of its pulses, and used Henrietta Leavitt's rule to figure out how bright it really was. Then he compared that to how bright it looked. The result was staggering. The star was so far away that there was no way it could be inside the Milky Way. The Andromeda Nebula was not a cloud of gas. It was an entire galaxy, millions of light years away, containing billions of stars of its own. In an instant, the universe got much, much bigger. But Hubble didn't stop there. He started measuring the distances to other galaxies. And as he did, he also looked at the light coming from them. Now, how do you look at light to see how something is moving? You use a spectrograph. You take the light from the galaxy and you pass it through a prism, which splits it into a rainbow, a spectrum. When you look closely at the spectrum of a star or a galaxy, you see dark lines. These are absorption lines. They are caused by atoms in the outer atmosphere of the stars absorbing very specific wavelengths of light. Hydrogen absorbs one wavelength, helium absorbs another, sodium absorbs another. It's like a barcode. Every element has its own barcode, and those barcodes never change except when the source of the light is moving. This is the Doppler effect. You've all experienced this with sound. When an ambulance is driving toward you, the siren sounds high-pitched. The sound waves are being squeezed together by the motion of the ambulance. Then as it passes you and drives away, the pitch drops. The sound waves are being stretched out. The same thing happens with light. If a galaxy is moving toward us, the light waves get squeezed together. The wavelength gets shorter, which shifts the light toward the blue end of the spectrum. We call this a blue shift. If a galaxy is moving away from us, the light waves get stretched out. The wavelength gets longer, which shifts the light toward the red end of the spectrum, and we call this a red shift. So Hubble looked at the barcodes of these distant galaxies. He expected to find some shifted to the blue, meaning they were moving toward us, and some shifted to the red, meaning they were moving away. If the universe was just a static collection of galaxies drifting around like a swarm of bees, You'd expect about half to be moving toward us and half to be moving away, but that's not what he found. Almost every single galaxy Hubble looked at was redshifted. They were all moving away from us. And there was a pattern, a very simple, very beautiful pattern. The farther away a galaxy was, the faster it was moving away. If a galaxy was twice as far away as another, it was moving away twice as fast. If it was 3 times as far away, it was moving 3 times as fast. Let's think about what this means. It doesn't mean that we are at the center of the universe and everyone is running away from us because they don't like us. It means the space between the galaxies is expanding. Think of a loaf of raisin bread baking in an oven. As the dough heats up, it expands. It stretches in all directions. If you are sitting on one of the raisins and you look at the other raisins, what do you see? As the dough expands, every raisin moves away from you. A raisin that is close to you moves away slowly because there is only a little bit of dough between you to stretch. A raisin that is far away moves away much faster because there is a lot of dough between you and all of that dough is stretching at the same time. No matter which raisin you sit on, you see the same thing. Every other raisin is moving away from you and the speed is proportional to the distance. The galaxies are the raisin. Space is the dough. The universe is expanding. When Einstein heard about Hubble's discovery, he went to Mount Wilson. He looked through the telescope himself, he looked at the data, and he realized he'd made a terrible mistake. The math had been right all along if he had just trusted his original equations from 1915, the ones without the cosmological constant. He could have predicted the expansion of the universe. He could have told the world years before Hubble looked through a telescope that the universe is dynamic, that it is growing, that it had a beginning, and that it is changing over time. It would have been one of the most stunning, mind-boggling predictions in the history of science. But he didn't trust the math. He let his human prejudice get in the way. He added a fudge factor to force the universe to fit his mental model of stability. Einstein immediately threw the cosmological constant away, and he set lambda back to 0. He later called the introduction of the cosmological constant his biggest blunder. He was embarrassed by it. It was an ugly, inelegant patch on a beautiful theory, and he was glad to be rid of it. And for decades, that was the end of the story. The cosmological constant was a historical curiosity, a footnote in textbooks. Einstein messed up, he fixed it, the universe is expanding, let's move on to other things. But nature is a lot more playful and a lot more subtle than we give it credit for. Let's skip ahead. We are going to go from the 1930s all the way to the late 1990s. By this time, technology had gotten much better. We had digital sensors, we had computers, we had the Hubble Space Telescope in orbiters, and we could see things that Edwin Hubble could only dream of. Astronomers wanted to answer a fundamental question about the expansion of the universe. We knew the universe was expanding, but we also knew it was full of stuff. It's full of galaxies, there's stars, dark matter, gas. All of that stuff has gravity. And gravity is attractive. It pulls things together. So if the universe is expanding, but it's full of gravity pulling inward, what should happen to the expansion? It should slow down. Think of throwing a ball up in the air. When the ball leaves your hand, it's moving fast. It's expanding away from the Earth. But as it goes up, the gravity of the Earth pulls on it. It slows down. It goes slower and slower. If you throw it hard enough, it might escape the Earth's gravity entirely and fly off into space. But even then, the gravity of the Earth will keep pulling on it, slowing it down as it goes. It will never speed up. Astronomers assumed the universe was doing the same thing. The expansion had to be slowing down. The only question was, by how much? Is there enough matter in the universe to eventually stop the expansion entirely and pull everything back together into a big crunch? Or is the universe so light, so empty, that the gravity will never quite stop it and it will keep expanding forever, but always at a slower and slower rate? To find out, we needed to measure how the expansion rate had changed over the history of the universe. We needed to look at galaxies that were very, very far away. Remember, when you look at something far away in space, you're looking back in time. Light doesn't travel infinitely fast. It travels at a finite speed, about 186,000 miles per second. The light from the moon takes about a second to get here. The light from the sun takes 8 minutes. The light from the nearest stars takes years. And the light from distant galaxies takes billions of years. So if you look at a galaxy that is 5 billion light years away, you aren't seeing it as it is today. You are seeing it as it was 5 billion years ago when the light left it. If we could measure how fast the universe was expanding 5 billion years ago and compare it to how fast it's expanding today, we could see the deceleration. We could see the gravity of the universe doing its work, slowing things down. Once again, we needed standard candles and so on, but Cepheid variable stars are too faint to see at those extreme distances of billions of light years. We needed a much brighter light, because we found it in type 1a, supernovae. These are not just regular stars, a type 1. A supernova is a massive explosion that happens in a binary star system. You have a white dwarf, a dead, dense star about the size of the Earth, but with the mass of the sun, and it's orbiting another star on types. The white dwarf pulls material off its companion star, piling it onto its own surface. But a white dwarf has a strict weight limit. It's called the Chandrasekhar limit, and it's about 1.4 times the mass of the sun. If the white dwarf gets even a tiny fraction heavier than that limit, the pressure inside can no longer support its own gravity. The star collapses, which triggers a runaway nuclear fusion reaction, and the whole thing blows itself to pieces in a fraction of a second. Because every type 1a supernova happens at exactly the same mass limit, every single one of these explosions releases the exact same amount of energy. They all have the same intrinsic peak brightness. They are the ultimate standard candles. They are so bright that they can briefly outshine an entire galaxy of billions of stars, meaning we can see them across the entire observable universe now. Two teams of astronomers started searching for these supernovae in the mid-1990s. It was incredibly hard work. You had to take pictures of thousands of galaxies night after night, compare them using computers, find the tiny point of light that wasn't there before, and then quickly use a spectrograph to measure its redshift before the explosion faded away. By 1998, both teams had collected enough data to make their calculation. They had measured the distances and the redshifts of dozens of ancient supernovae. They sat down at their computers, ran the numbers, and they got an answer that made absolutely no sense. As long as the distant supernovae were too faint. Think about what that means. If they were too faint, it meant they were further away than they should have been based on the rate of expansion we measure today. If that expansion had been slowing down, the gravity hadn't been slowing the universe down, the expansion was speeding up. The universe is accelerating. This was a shock to the system. It was as if you threw a ball up in the air, watched it slow down for a second, and then suddenly saw it rocket off into the sky, going faster and faster and faster, as if some invisible engine had kicked in. How do you explain that? What could possibly cause the entire universe to fly apart faster and faster? Gravity pulled. It doesn't push. To get an acceleration, you need some kind of repulsive force. Right? You need a pressure that pushes outward on the scale of the entire cosmos for four. And where does that lead us? Right back to Albert Einstein's desk in Berlin, right back to the Greek letter lambda, right back to the cosmological constant. The term that Einstein added to force his equations into stillness, the term he threw away in embarrassment and called his greatest mistake, was exactly what we needed to explain the acceleration of the light. Only Einstein had used it to hold the universe still. But if you make lambda just a little bit bigger than what is needed for a static balance, it doesn't just hold the gravity at bay, it wins the tug of war. It pushes the universe into an accelerating expansion. And so Einstein was wrong about the universe being static, but his mathematical formulation of the cosmological constant was completely right in that his blunder turned out to be the real-world description of our universe. Today, though we don't call it the cosmological constant anymore, although we still use the letter lambda in our equations, we call it dark energy. Why dark energy? Because we don't know what the hell it is. It's a name we give to our ignorance. It's dark not because it looks black, but because it's completely invisible to our telescopes. It doesn't emit light, it doesn't absorb light, and it doesn't reflect light. We only know it's there because of its gravitational effect on the expansion of the universe. And here's the most mind-blowing part of the whole thing. Dark energy is not a small minor player in the cosmic game. If you add up all the mass and energy in the universe, you find that everything we can see, all the stars, the planets, the gas clouds, the trees, the oceans, the buildings, you and me, makes up only about 5% of the total, 5%. Another 25% or so is what we call dark matter. That's another mystery. It's some kind of invisible matter that has normal attractive gravity but doesn't interact with light. We see its effects in the way galaxies rotate and how they clump together. The remaining 70% of the universe is dark energy. 70%. The dominant stuff in the universe is this mysterious energy that is pushing everything apart, and we are completely in the dark about what it actually is. We are like cosmic minorities in our own universe, living in a tiny 5% sliver of normal matter while the main show is being run by things we can't even see. So let's ask the obvious question, what could dark energy be? The simplest, most elegant explanation, the one that matches the data we have right now, is that it is indeed the energy of empty space. It is the cosmological constant dark. Now, you might think, wait a minute, how can empty space have energies? Empty space is not, if I take a box and I pull all the air out of it, and I shield it so no radiation can get in, and I cool it down to absolute zero so there's no heat. What's left in the box? Nothing, right? Well, if you ask classical physics, yes, nothing is left. The box is empty. But if you ask quantum mechanics, the answer is very different. Quantum mechanics is the physics of the very small. And in quantum mechanics, there is a fundamental rule called the Heisenberg uncertainty principle. One of the things this principle tells us is that you can never know both the energy of a system and the time at which it has that energy with absolute precision. What this means for empty space is that the energy of a vacuum can never be exactly, precisely zero. If it were exactly zero, that would be a state of perfect certainty which the laws of physics do not allow. So instead of being a boring, empty void, the quantum vacuum is a wild, seething, boiling soup of activity. Quantum fields are constantly fluctuating. Particles are constantly popping into existence out of the vacuum, borrowing energy from the uncertainty principle, existing for a tiny fraction of a second, and then colliding with their antiparticles and disappearing back into the vacuum. They are called virtual particles. They aren't just a mathematical trick. We have measured their effects in the lab. There is a phenomenon called the Casimir effect, where if you put two uncharged metal plates very close together in a vacuum, the fluctuations of the vacuum outside the plates are slightly different from the fluctuations inside, which creates a measurable force that pushes the plates together. We have also seen their effects in the energy levels of the hydrogen atom in what's called the Lamb shift. So we know these virtual particles are real. The vacuum of space is alive with quantum energy. And here is where we run into the biggest, most beautiful, most embarrassing disaster in the history of modern physics. If the vacuum has energy, then according to Einstein's E equals mc squared, that energy must have a mass equivalent. And since it has mass, it must have a gravitational effect. It must curve space-time. It must act exactly like the cosmological constant. So being physicists, we decided to calculate how much energy should be in the vacuum. Based on our quantum theories, we add up all the possible fluctuations of all the quantum fields we know about, the electromagnetic field, the electron field, the quark fields, all of them. Now, if you do that calculation without any limits, the answer you get is infinity. That's obviously not right. So you have to be clever. You say, well, our current theories of physics probably don't work all the way down to infinitely small distances. They probably break down at a certain scale called the Planck length, which is the scale where the quantum effects of gravity become important. So you stop your calculation there. You use the Planck length as a cutoff. When you do that, you get a number. And that number is huge. It is about 10 to the power of 120 times larger than the value of the cosmological constant we actually observe in the universe. Let's write that out in our heads. A 1 followed by 120 zeros. This is not a small error. This is not like being off by a few percent or even a factor of 2. It is the worst theoretical prediction in the entire history of science. It is so wrong that it is almost comical. If the vacuum energy were actually as big as quantum mechanics predicts, the outward push would have been so violent that the universe would have expanded faster than the speed of light in the first tiny fraction of a second after the Big Bang. Space would have been stretched so thin, so fast that no two atoms could ever have met. No stars could have formed, no galaxies, and no planets, no people. But we are here. The universe does exist. Stars do exist, and the expansion of the universe is accelerating, but it is accelerating very, very gently. The actual value of the cosmological constant is incredibly small. It's just barely above 0. So we have this massive gaping hole in our understanding of reality. So we have general relativity, which works perfectly for the big stuff, and we have quantum mechanics, which works perfectly for the small stuff. But when we try to put them together to explain the vacuum of space, they give us an answer that is wrong by 120 orders of magnitude. What does this tell us? It tells us that we are missing something fundamental, that there is a bug in our code. There is some piece of the puzzle that we haven't seen yet. Maybe gravity doesn't feel the vacuum energy the way we think it does. Maybe there is some kind of cancellation mechanism that we haven't discovered yet, some symmetry of nature that forces the positive and negative vacuum energies to cancel each other out almost completely, leaving only a tiny, tiny remainder. Or maybe our entire way of calculating vacuum energy is wrong. And this is what makes physics so exciting. Some people get discouraged when they hear about a problem like this. They think, oh, we don't know anything. The scientists are all confused. But to a physicist, this is the holy grail. If everything worked out perfectly, if the math matched the observations to 10 decimal places and there were no mysteries left, we'd be done. We'd just be engineers, applying the formulas we already knew. Physics would be dead. It's the discrepancies, the places where the theories break down and scream at us that they don't work, that show us where the next big discoveries are going to be. That is where the next Einstein, the next Newton, is going to find their work. Now, let's think about what this means for the future. If the cosmological constant is indeed constant, if this dark energy stays exactly the same forever, then the fate of our universe is sealed. And it is a very strange, very lonely fate. Right now, we live in a golden age of cosmology. We look out at the sky and we can see thousands of other galaxies. We can see the cosmic microwave background, the leftover heat from the Big Bang, and we can map the structure of the cosmos. But as the universe continues to accelerate, the space between galaxies will grow faster and faster. Now our local group of galaxies, the Milky Way, Andromeda, and a few dozen smaller ones, are held together by their mutual gravity. We are close enough that gravity wins the local tug-of-war. Eventually, the Milky Way and Andromeda will merge into one giant galaxy. But the other galaxies, the ones outside our local group, will be pushed away from us faster and faster. Over time, the speed of recession will exceed the speed of light. Now, you might say, wait, I thought nothing can travel faster than light. That is true through space, what? But space itself can expand at any speed it wants. There is no speed limit for the expansion of space-time. As those galaxies cross the horizon where they are moving away from us faster than light, the light they emit will never be able to reach us. They will disappear from our view. One by one, the distant galaxies will slip over the cosmic horizon. The sky will go dark. If there are astronomers living in our merged galaxy 100 billion years from now and they look up at the sky with their telescopes, they won't see any other galaxies. They won't see the cosmic microwave background. They will see only empty black space. They will have no way of knowing that the Big Bang ever happened. They will have no way of knowing that the universe is expanding. They will write textbooks concluding that their galaxy is the entire universe, static, lonely, and surrounded by an infinite void. They will be trapped in the very static universe that Einstein tried to invent, but it will be a real desolate prison. And then, as the stars burn through their nuclear fuel, they will begin to die. Red dwarfs will fade into black dwarf. The gas clouds will be exhausted so no new stars can form. Black holes will swallow up the remains of dead stars, and then over incredibly long spans of time, even those black holes will slowly evaporate through Hawking radiation. The universe will become a cold, dark, uniform soup of individual particles separated by distances so vast that they can never interact. This is what we call the big freeze, or the heat death of the universe. It is a state of maximum entropy, where nothing ever happens because there is no energy difference left to do any work. It is a heavy, almost depressing thought. But is it definitely true? We don't know. And the reason we don't know is that we don't know if dark energy is truly constant. Remember, we have only been measuring this acceleration for a few decades. In cosmic terms, that is less than a blink of an eye. We are like mayflies, which live for a single day. Trying to write a theory of the seasons based on what happens between 2 and 3 o'clock on a Tuesday afternoon. Maybe dark energy is not a constant. Maybe it is a dynamic field that changes over time. If dark energy is a field, some physicists call it quintessence, it could behave very differently in the future. Maybe the field will eventually decay. Maybe it will slow down, stop, and turn off. If it does, then the gravity of the matter in the universe could take over again, slow the expansion down, and pull everything back together in a big crunch. Or maybe the field will become even stronger. If dark energy increases in strength over time, it could eventually become so powerful that it doesn't just push galaxies apart. It could overcome the gravity holding individual galaxies together, tearing stars away from their orbits. Then it could overcome the gravity holding solar systems together, pulling the Earth away from the sun. And finally, it could overcome the electromagnetic and nuclear forces holding atoms together, ripping apart molecules, atoms, and the very fabric of space-time itself. And we call this the Big Rip. Or maybe it will fluctuate, bouncing back and forth, causing the universe to expand, contract, and expand again in an eternal cycle. The truth is, we don't have enough data yet to be sure, but we are working on it. Astronomers are building new instruments right now, space telescopes, like the Nancy Grace Roman Space Telescope, ground-based surveys like the Vera C. Rubin Observatory, and instruments like the Dark Energy Spectroscopic Instrument, which are mapping millions of galaxies in 3 dimensions to measure the history of cosmic expansion with unprecedented precision. They are looking for any tiny deviation from a perfect constant. They are looking to see if dark energy was slightly different 8 billion years ago compared to what it is today. And if they find a deviation, if they find that dark energy is changing, it will open up a whole new realm of physics. It will give us the first real clue about the underlying mechanism of this cosmic mystery. Let's step back and think about the nature of this entire journey. It shows us something profound about how science works. Science is not a monument of unshakable facts. It is a process. It is a way of thinking. It is a journey where we are constantly making mistakes, correcting them, and then finding out that our corrections were wrong in an even more interesting way. Think about the irony of Einstein's path. He writes down his equations of gravity. They are perfect. They are beautiful. But he doesn't like where they are pointing. He has a psychological block. He wants a static, comfortable universe. So he adds a term to stop the movement. Then when he is confronted with the evidence that the universe is indeed moving, he feels foolish. He throws the term away. He wants to delete it from his permanent record. And then decades after he is gone, we look closer at the universe and we find out that the term he added was not a mistake at all. The universe actually uses it. It is the most important number in the cosmos. He was right, then he thought he was wrong, and then it turned out he was right for the wrong reason. And now we are left trying to figure out why he was right. You see, nature doesn't care about our aesthetic preferences. Nature doesn't care if we think an equation is elegant or if we think a universe should be quiet and unchanging. Nature just does what it does. The math is our only guide, and the math has a funny way of being smarter than we are. When you write down a fundamental equation like the Einstein field equations, you aren't just writing a description of your own ideas. You are tapping into the deep structure of reality. And that structure has consequences that you might not expect, consequences that you might even fight against, but which turn out to be true anyway. It's like when Dirac wrote down his equation for the electron. He was trying to combine quantum mechanics with special relativity. He wrote down the math and he noticed that the equation had two solutions, just like the equation x squared equals 4 has two solutions, +2 and -2. One solution described the normal electron with negative charge. The other solution described a particle with positive charge, but otherwise identical properties. Dirac didn't know what to make of it. No such particle had ever been seen. He tried to explain it away, thinking maybe it was the proton. But the math said no, it has to have the same mass as the electron. He hesitated. He was worried the math was giving him a nonsense result. But he trusted the equation because he published it. And a few years later, Carl Anderson discovered the positron, the antimatter counterpart of the electron in cosmic rays. The math had predicted the existence of an entirely new form of matter before anyone had ever seen it. Einstein's field equations did the same thing. They tried to tell him that the universe was dynamic. They tried to tell him that space-time could expand and contract. He resisted, but the math was right. So what is the lesson for us? The lesson is that we must have the courage to trust our equations, even when they point to things that look crazy or uncomfortable or weird. And we must have the humility to admit when we are wrong and the curiosity to look at our mistakes to see if there is some hidden truth buried inside them. I have spent my whole life playing with equations, trying to understand how light and matter interact. And I can tell you that the most satisfying feeling in the world is not when you get the answer you had expected. The most satisfying feeling is when you get an answer that surprises you, an answer that makes you say, wait a minute, that can't be right. And then you check your work, and you check it again, and you realize it is right. And you have to change your entire way of thinking about the world to accommodate this new truth. That is what happened to Einstein. That is what happened to the astronomers in 1998. And that is what is going to happen to the next generation of physicists who tackle this dark energy problem. We have this beautiful, mysterious universe. It is 95% unknown to us. It is expanding, it is accelerating, and it is governed by forces we are only just beginning to name. We are like children standing on the edge of a vast, dark ocean, looking at the ripples on the shore. We've found a few pebbles, we've mapped a few waves, but the deep water is still waiting to be explored. And that is not a cause for despair. It is a cause for excitement. It means there are still great discoveries to be made. It means the story of physics is not finished. It is just getting started. So don't be afraid of the mysteries. Don't be afraid of the things we don't understand. Embrace the confusion. Look for the discrepancies, because that is where the truth is hiding. And who knows? Maybe one of you will be the one to find the key that unlocks the mystery of the quantum vacuum, the one who reconciles the big and the small, and explains why Einstein's biggest blunder was the most important thing he ever did. Keep your eyes open. Keep asking questions. And don't ever let anyone tell you that we have it all figured out. We don't. And that is the most wonderful thing of all. Thank you. Today's lecture is about quantum entanglement and why it terrifies physicists. Let's start with a problem that bothered Einstein until the day he died. Not because he was slow, he was one of the sharpest minds we ever had, but because he couldn't stomach the idea that nature might be playing dice with the fundamental rules of how things work. He wanted a world that was local, a world where things happen here because something pushed them here, not because something happened on the other side of the moon. I remember sitting in my office at Caltech staring at a chalkboard covered in scribbles, trying to explain this to a student who kept asking me why the math worked the way it did. I didn't have an answer then. I don't have a perfect answer now, and that is exactly what makes this subject so peculiar. Think about a pair of gloves. You have two gloves, one left, one right. You put them in two separate boxes. You take one box to New York and send the other to Timbuktu. Now, the person in Timbuktu opens their box. They see a left-hand glove. Instantly, they know that the box in New York contains the right-hand glove. There is no mystery here. You don't call up the physics department and scream about a breakthrough. You just have a pair of gloves. The information about which glove which was already fixed the moment you packed the boxes. Physics used to be like that. We assumed that if you had two particles, they had definite states before you measured. If you measured the spin of one and it was up, the other had to be down. The state was determined before you even looked. That is what we call local realism. It is the bedrock of how we experience the world. You touch a hot stove, your hand burns. The heat transfers because the molecules in your skin hit the molecules in the stove. Everything touches everything else to make things happen. But then the quantum mechanics showed up, and it turned out that the world doesn't behave like a pair of gloves. Imagine you have two electrons. You create them in such a way that their total spin is zero. They are entangled. Now you separate them. You send one to the far side of the universe, and you keep one right here in the room. According to the old school way of thinking, each electron has its own properties, its own spin, just waiting to be measured. But quantum mechanics says no. Before you measure it, that electron doesn't have a spin. It is in a superposition. It is, in a sense, both up and down at the same time. It is a blur of probability. The moment you measure the one in your room, the probability wave collapses. You see up. And at that exact, precise, instantaneous moment, the other electron, the one on the other side of the universe, becomes down. It happens faster than the speed of light. It happens without a signal passing between them. If you try to tell me there is a wire connecting them or a ghost signal flying through space, the math says you are wrong. The correlation is perfect. And it is this spooky action at a distance, as Einstein called it, that makes the whole thing feel like a violation of the rules. When I was working at Los Alamos, we spent a lot of time thinking about how information moved. We had these massive problems to solve, trying to figure out if an implosion device would actually work. But we had to trust that things were local. If you change a parameter here, the result changes there because of a sequence of events. If the world were governed by entanglement in our daily lives, building a bomb would be impossible because you could never guarantee the state of the material. You would just be hoping the universe decided to cooperate. Einstein hated this. He argued that quantum mechanics must be incomplete. He thought there were hidden variables. He believed there was a secret instructions list inside the particles, something we weren't seeing, which determined the outcome beforehand. Like the gloves, if we could only see the hidden variables, the spookiness would disappear. For a long time, we couldn't test this. It was just philosophy. People would argue in the halls, drink coffee, and draw diagrams, but nobody could build an experiment to settle it. Then a fellow named John Bell came along. Bell did something brilliant. He didn't just guess. He proved that there is a limit to how correlated two things can be if they are governed by local hidden variables. He created an inequality, a mathematical line in the sand. If the world followed the gloves theory, the Einstein theory, the correlation would stay below a certain number. If the world followed the quantum theory, the correlation would cross that line, and it was one of the most important moments in the history of physics. We finally had a way to ask nature the question directly. I recall when the experiments finally started to get precise enough to test this. You have to set up these polarizers. You measure the spin of particle A along one axis and particle B along a different axis. You run the number. You check if the correlations violate the inequality. And every single time we do it, nature crosses the line. It doesn't care about our intuition. It doesn't care that Einstein thought it was wrong. It just does what it does. Now, why does this terrify people? Why does it bother us so much? It's because of what it implies about space. We think of space as a stage, a stage where things are separated by distance. If I am here and you are there, I cannot influence you instantly. I have to throw a ball. The ball has to travel. That takes time. Space separates us, and that separation prevents us from being one thing. Entanglement suggests that at a very fundamental level, distance might be an illusion. If two particles can be correlated in a way that ignores the distance between them, maybe they aren't actually separated. Maybe the idea of here and there is just a way we carve up the world, but the world itself doesn't recognize those boundaries. I remember thinking about this while walking through the tunnels in Ithaca. It's an uncomfortable feeling. You want to believe in an objective reality where things exist independently of whether you are looking at them. You want a world where an electron is just a little billiard ball with a specific direction of spin. But the math and the experiments, they don't let you keep that comfort. The math says that the particles share a single wave function. They are part of one system. You can't talk about particle A without talking about particle B. They are not two things, they are one thing, just stretched across the universe. So is there a secret message passing between them? Can we use this to talk to Mars instantly? Here's where the confusion usually hits. People get excited. They think, aha, we can send messages faster than light. But you can't. If I measure my electron and I get up it, I know the other one is down. But I cannot force my electron to be up. It's random. I can't control the outcome. And since I can't control the outcome, I can't send a signal. The person on the other end sees a random sequence of up and down. They don't know if I measured mine or not, and they only realize the correlation when they bring their data back to my lab and we compare the lists. So information is not traveling faster than light. Causality is preserved. The universe is still safe in a sense, but the connection is still there. This creates a split. We have the shut up and calculate crowd. Like they say, look, the math works. The predictions are accurate. Just use the equations and don't worry about the philosophy. And then you have the ones who keep digging, the ones who get ulcers over it. I suppose I've always been in the second camp. I don't want to just calculate it. I want to feel the physical mechanism. I want to see the gears turning up. And in entanglement, the gears are hidden. Or maybe the gears aren't there at all. Let's try to visualize it differently. Imagine two dancers. They are on opposite sides of a stage hidden behind curtains. They have never rehearsed. They don't have a plan. But the moment the curtains rise, they start dancing in perfect synchronization. If one spins left, the other spins right every single time. You would assume they were whispering to each other, or they had a secret agreement, or they were practicing for weeks. But what if they weren't? What if they were just connected? That is the quantum state. It makes me think of the early days of quantum mechanics, back when we were still figuring out the basics. Bohr, Heisenberg, Schrödinger, they were all trying to fit this into a box. They were trying to make it match the world we see. But the world we see is a macroscopic limit. It's a fuzzy, averaged out version of the truth. When you zoom in, when you look at the electron, the billiard ball is gone, and the certainty is gone. Is it possible that we are missing a layer? Is it possible that there is a theory deeper than quantum mechanics? It's something that explains why this entanglement happens? Maybe. Many people have tried to find it. They've written papers, built models, proposed all sorts of weird stuff, but so far nothing has replaced the quantum theory. It remains one of the most accurate descriptions of reality we have ever produced. The discomfort comes from the feeling that we are missing something fundamental. We feel like we are looking at the shadow of a much larger, more complex shape, and we are trying to guess the shape just by looking at the shadow on the wall. Think about the implications for gravity as there are. We don't have a good theory of quantum gravity. General relativity describes a smooth, curved space-time. Quantum mechanics describes a choppy, probabilistic universe. They don't get along. They fight. And entanglement sits right at the center of that fight. Some of the brightest people today are trying to figure out if space-time itself is built out of entanglement. Imagine that. The distance between me and the back wall, the fabric of the cosmos, the shape of the universe, it might all be a byproduct of these quantum links. It sounds like science fiction, but that's how physics works. You start with something impossible, you test it until you're blue in the face, and then you accept that reality is just stranger than you thought. Let's go back to the experiment for a second. Suppose you measure the polarization of photons. If you have a photon source, it emits two photons in opposite direction. You put a filter, a polarizer in the path of each photon. You can rotate the angle of the polarizer. If you align both polarizers at the same angle, you get perfect correlation. But if one lets light through, the other does too. If you rotate one, the correlation changes according to a specific law. The cosine squared of the angle different. And this is the key. The way the correlation changes is the fingerprint of quantum mechanics. The hidden variable theories, the local realist theories, they predict a different curve, a linear curve or something else. They don't predict that specific cosine squared curve. When we measure it, the curve follows the quantum prediction. It's exact. So we know the particles are linked in a way that classical objects cannot be. We know that the state of one is not defined until the measurement happens, and we know that this behavior is robust. We can do this with photons, with electrons, with ions, even with large molecules. The question remains, why? Why does nature do this? I used to go down to the local diner just to get away from the office. I'd sit there with a coffee and a notebook. I'd watch the cars go by, the people walking, the rain hitting the window. It all feels so continuous, so solid. You have a cup of coffee. It stays a cup of coffee, and it doesn't become a cloud of probability. No, it doesn't get entangled with the coffee in the next town over. The macro world is different from the quantum world because of decoherence. When a quantum system interacts with the environment, bumping into air molecules, light, dust, the entanglement leaks out. It gets lost. It gets smeared across the environment. So for big things like coffee cups and cars, the quantum effects are washed out. They are effectively hidden. But that doesn't mean they aren't there. It just means we are blinded by the sheer noise of the world. If we could isolate a system perfectly, if we could keep it cold and quiet, the entanglement would be visible. We have technology now that lets us do that. We have traps for atoms. We have superconducting circuits. We are creating these entangled states on purpose. We are playing with them. We are building computers that use this spooky behavior to solve problems that would take a normal computer the age of the universe to crack. So we are moving from this is a philosophical nightmare to this is a tool. We are engineering the spookiness, but even as an engineer, even as someone who builds the circuits, the feeling of unease persists because we are manipulating something we don't fully understand. We are like children playing with a radio. We know which knob turns the volume up and we know which switch changes the station, but we don't know how the radio waves travel through the air. We don't know what the field is. That is the humble truth. We have the rules, the Schrödinger equation, the density matrices, the operators, but we don't have the intuition. We don't have the why. I remember once I was trying to explain to a high school class how the double slit experiment works. It doesn't work. You fire electrons at two slits and you get an interference pattern. It's like waves in water. If you look at which slits the electron goes through, the pattern disappears. It becomes two bands. The student asked, but where is the electron when you aren't looking? And I told him, you shouldn't ask that. I was half joking, but I was also serious. The question assumes the electron is somewhere. It assumes that somewhere is a meaningful concept for an electron. But in the quantum view, somewhere is a feature that emerges from the measurement. Before the measurement, the electron is a range of possibilities, a wave of potential, and entanglement is just the double slit experiment turned up a notch. It's the same refusal of nature to be pinned down. It's the same insistence that the system is global, not local now. Are there limits to this? Could the whole universe be entangled? Some physicists argue that the entire universe started as a single point, a singularity. If that's true, then everything in the universe started in an entangled state. Maybe in some deep, profound sense, everything is still entangled. Maybe the reason gravity acts the way it does is because the particles are still to some degree maintaining that initial ancient connection. That is a bold thought. It's speculative, but it's the kind of thought you have when you stare at these equations long enough. Let's look at the terrifies part of the title. Why should physicists be afraid? Fear is the wrong word. It's more like an itch you can't scratch. It's the feeling of being wrong about something fundamental. We like to think that we have made progress. We went from Aristotle to Newton, from Newton to Maxwell, from Maxwell to Einstein. Each step was a refinement. Each step gave us more control, more power. But quantum mechanics feels like a discontinuity. It feels like we walked into a dark room and found that the floor was made of jello. You can stand on it for a moment, you can walk across it if you're careful, but you can't trust it to be a solid floor. And that uncertainty, that instability, it makes us uncomfortable. We want the floor to be rock. We want the universe to be understandable in terms of simple, local, solid objects. But the universe doesn't have to be what we want. I've had students come to me, brilliant kids, really sharp, and they ask, can we just interpret it differently? Can we use the many worlds interpretation? Can we use pilot waves? Can we use collapse models? And I tell them, sure, pick your poison. Because all of these interpretations lead to the same math, and they all predict the same experimental results. The math is the only thing we have that works. The interpretation, they are just stories we tell ourselves to help us sleep at night. They are the pacifiers we use to deal with the fact that the math is counterintuitive. Many worlds, it says every time a measurement happens, the universe splits. Every possible outcome happens in a different non-interacting branch of reality. It saves locality, but at the cost of an infinite number of universes. Is that a price you want to pay? Pilot waves, it says there are particles that really do have definite positions, and they are guided by a hidden wave that exists in the background. It saves realism, but at the cost of non-locality. The wave has to know about everything, everywhere, instantly. Collapse models, they say there is a physical process that causes the wave function to snap into a single state randomly. It solves the measurement problem, but it requires us to modify the laws of physics to add a term to the equation that we haven't seen yet. Each one of these takes something we hold dear and breaks it. Each one requires a sacrifice. And that is why entanglement is terrifying, because it forces us to choose what we are willing to give up. Are you willing to give up locality? Are you willing to give up realism? Are you willing to give up the idea that the universe is simple? I think the reason I spent so much time on this, the reason I played with the path integrals, the diagrams, the sum over histories, was because I wanted to find a way to make it all fit together without the sacrifice. I wanted a way to calculate, to predict, to understand, without having to invent 100 universes or hidden ghost waves. I didn't find it. I don't think anyone had. Maybe the point isn't to fix it. Maybe the point is to live with it, to accept that nature is just like this. Think about the way you learn to swim. You don't learn by reading a book on fluid dynamics. You jump in, you flail, you get water up your nose, you panic, you try to fight the water, you try to grab onto the water to hold yourself up, and that doesn't work. The water doesn't care. Then eventually you stop fighting. You relax and you let the water support you. You realize the water has its own way of moving and you have to move with it, not against it. Physics is like that. We spend years trying to force nature to be what we wanted it to be. We wanted it to be logical. We wanted it to be intuitive. We wanted it to be local. And then one day, you stop. You realize the universe doesn't owe you an explanation that makes sense to your brain, which evolved to hunt for food and avoid predators on the African savanna. Why should our brains be capable of understanding the fundamental structure of reality? Dude, that's a miracle if you think about it. So when you see a paper about entanglement, or you hear someone talking about quantum teleportation, don't get hung up on the teleportation or the spookiness. Those are just words. They're just metaphors. The reality is the correlation. The reality is the math. The reality is that the universe is linked in ways that defy our everyday logic. And that is a beautiful thing. It means the world is richer, deeper, and more surprising than we ever imagined. Let's dig a bit deeper into the history. When Einstein, Podolsky, and Rosen, the EPR paper, came out, they were really trying to prove that quantum mechanics was incomplete. They thought they had caught the theory in a lie. They said, look, if we can predict the state of particle B by measuring particle A, then particle B must have a defined state all along. And if quantum mechanics says it doesn't, then quantum mechanics is wrong. It was a logical argument. If A is true and B is true, then C must follow, and it was perfectly sound. The only problem was the premise. The premise that objects have defined states turned out to be false. It's like asking, if I have a fair coin, what is the outcome of the flip fee solve? The answer is the coin doesn't have an outcome until it lands. But they were arguing about the nature of the coin. And they were saying, no, the coin must have a side face up, even while it's in the air. You just haven't looked at it yet. And quantum mechanics was saying, no, the coin is a blur of heads and tails while it spins. It is both. It is neither. It is a probability distribution. Einstein couldn't accept that. He wanted the coin to be heads or tail, but he wanted the world to be definite. Now imagine if you could flip two coins at the same time in different rooms and they always landed on the same side, even though each coin was a fair flip. Even though you couldn't control it, that would be weird, right? And you would say, hey, there's a mechanism linking these coins. But in quantum mechanics, it's not even that. It's like the coins are flipped and they are both heads and tails simultaneously, and only when you stop them do they settle. And the link ensures that if one settles on heads, the other settles on heads. It's not just that they are correlated, it's that they are undefined until the correlation is tested. This is the hardest part to wrap your head around. It's the part that makes students stay up all night. If the particle doesn't have a spin, how does it know which way to spin when the other one is measured? It doesn't know. That's the wrong word. Knowing implies a process, a calculation. The system just is. It satisfies the constraints of the wave function. It's a global solution to a local problem. I used to use the analogy of a drum. If you hit a drum, the sound isn't localized to just one point on the skin. The whole drum head vibrates. Every part of the drum moves in harmony with every other part. You can't say that this part of the drum is vibrating because I hit it, and that part is vibrating because, well, I don't know. The vibration is a property of the whole drum. Entanglement is like that. The particles are the drum. The measurement is the tap. The correlation is the sound. This also explains why we can't send signal. You can't play a melody on the drum by only touching one point and expecting that to be the only thing that happened. If you tap the drum, the whole surface responds. If you tap it somewhere else, you get a different sound. But if you're trying to send a message to someone on the other side of the drum, you can't control the specific vibration pattern in a way that encodes information, because the drum is a physical system that follows its own laws. It's a bit of a stretch, this analogy, but it's better than the hidden variable stuff. I think the reason we keep coming back to entanglement is that it hints at something we haven't solved yet. It's a loose thread. We pull on it, and the whole sweater starts to unravel. Gravity, thermodynamics, information theory. It all seems to point back to this weird entangled structure. There is a concept called black hole information paradox. You throw a book into a black hole. The information about the words in the book, the atoms, the state, the entanglement, what happens to it? Does it vanish? If it vanishes, that violates the laws of quantum mechanics, which say information must be preserved. And if it stays, where is it? Maybe it's encoded on the surface of the black hole. Maybe it's entangled with the Hawking radiation that comes out. This is the frontier. This is where the best minds in the world are currently beating their heads against the wall. And it's all at the bottom about entanglement. I remember meeting some of these people at conferences, of course. They have this intensity, this wild look in their eyes. They aren't interested in the easy stuff anymore. They want to know what the universe is made of. And they're all betting on entanglement. Is it possible that space itself is woven out of entanglement? That the reason we have space and time is because we have these quantum correlations? That is a deep thought. It implies that before there was space, there was entanglement. Before there was a where, there was a relationship. Think about that. A relationship without a place. It sounds like poetry, but the math is starting to look that way. The geometry of space-time seems to be related to the entropy of entanglement. The more entangled things are, the more space you have. If this turns out to be true, then Einstein was wrong about the gloves, but he was right that gravity is geometry. It's just that the geometry isn't the fundamental thing. The geometry is the emergent thing. The geometry is the shadow. The entanglement is the light. When I was a kid, I used to fix radios. I loved taking them apart, seeing how the wires connected and how the resistors and capacitors interacted to create the sound. I wanted to understand the machine. Entanglement is like the ultimate radio. It's a machine that works in ways that aren't obvious from the wiring diagram. You look at the wires and you say, this shouldn't work. And then you turn it on and the music plays. And you realize the wiring diagram is wrong. The wires aren't just wires. They are paths for a field. They are part of a larger structure. I think that is the lesson of entanglement. Our wiring diagrams that are classical physics, our common sense, and our intuitions, like a just approximation. They are useful for building bridges and radios and airplanes. But when you get to the level of the electron, the wiring diagram breaks. And you shouldn't be afraid of that. You should be excited. Because if the world was simple, and if the world were just a bigger version of the things we see every day, it would be boring. The fact that it's weird, that it's spooky, that it defies our common sense, that is what makes it interesting. That is why we do physics, not to confirm what we already know, but to find out what we don't know, to push the boundaries, to see where the map ends, and then to walk off the edge into the unknown. I sometimes wonder what Einstein would think if he were alive today. He died before the experimental proof of Bell's inequality. He died still fighting the quantum theory. I like to imagine him reading the results of the aspect experiment. I think he would have been frustrated, sure. He would have hated it. He would have tried to find a loophole. He would have spent weeks, months, years trying to prove the experiment wrong. And then, when he realized he couldn't, I think he would have been the first one to say, well, then, we have a lot more work to do. He was a scientist, after all. He followed the evidence, even when he didn't like the result. That is the integrity you need. You have to be willing to be wrong. You have to be willing to look at the data and say, okay, my intuition was wrong. The universe is not the way I thought it was. Most people can't do that. They cling to their ideas. They protect their theories like they are guarding a treasure. But in science, the treasure is the truth. And the truth doesn't care about your theories. The truth just is. So don't worry about understanding it perfectly. Nobody does. Feynman, Einstein, Bohr, we were all just trying to catch up to the reality of the situation. We were all just students in a way. The mystery is the point. The question is the point. And if you ever find yourself thinking you understand quantum mechanics, you're probably wrong. You're probably just looking at the math and mistaking it for the reality. You have to keep the itch. You have to keep the question alive. Because the moment you say, I understand, you stop learning. And that is the death of science. We have this tendency as humans to try and label things, to put them in categories, to say this is a wave and this is a particle. But nature doesn't have labels. Nature doesn't have categories. Nature just has behavior. Entanglement is a behavior. It's a way that matter acts. It's a way that the universe maintains consistency across distances. We don't have to call it non-locality or spooky action. We can just call it the way things are. I think that's the most Feynman-like advice I can give. Don't get hung up on the words. Don't get hung up on the labels, and look at the phenomenon. Look at the data. Look at the experiment. And if it contradicts your common sense, don't throw out the experiment. Throw out your common sense. Your common sense was built for throwing rocks and dodging lions. It wasn't built for understanding the fundamental structure of space and time. It's a miracle it works at all. There is a moment in the lab, right before you take the data, when you have everything set up, the equipment is humming, the lasers are aligned, the detectors are ready. You are about to ask nature a question, and you don't know the answer. That is the best moment. That is the moment of pure possibility. And entanglement gives us so many questions. We can test it with different particles. We can test it with different distances. We can test it with different conditions. We can test it until we understand the limits. And then maybe we will see the next layer. Maybe we will see what lies beneath the entanglement. I suspect that the answer will be something simple. It's something so simple that we will look back and laugh at how confused we were. We will say, of course, and it was obvious. Why didn't we see it sooner? But until then, we have the mystery, and we have the math, and that is enough. Let me talk about the locality assumption again. It's really the core of the problem. We assume that for an event at point A to affect an event at point B, there must be a chain of events connecting them. The speed of light is the speed limit of these causal chains. Nothing can go faster. So when we see an instantaneous correlation, we feel like the speed limit has been violated. We feel like the law has been broken. But the speed limit applies to the transmission of information. It applies to sending a message. If I try to send you a bit of data, I have to obey the limit. But entanglement isn't about sending a message. It's about the state of a system. The system is already there, and so it's already prepared. It's like having a deck of cards. You shuffle the deck, you split it into two halves. You give one half to me and one to you. You fly to New York. I stay in London. We both open our halves. We realize that the cards are arranged in a specific way. The order is correlated by color. Did the cards communicate at the speed of light to arrange themselves? No. The order was established when we shuffled the deck. The difference in quantum mechanics is that the shuffling happens in a way that doesn't define the cards until we look. It's a shuffling that exists in a state of indefinite potential. But the core insight is that the information isn't traveling, Pitha. The correlation is inherent to the system. So the locality isn't violated because there is no communication. There is no signal. There is no information transfer. If you understand that, if you can really feel that distinction, then the spooky part starts to fade away. It's still weird. It's still counterintuitive, but it's not magic. It's not breaking the laws of physics. It's just physics doing something we didn't expect. It's like when we discovered that light is a wave. Before that, we thought light was a stream of particles. Newton thought it was particles. And then we saw interference pattern, and we said, oh, it's a wave. And then later, we saw the photoelectric effect, and we said, oh, it's particles. And then we realized it's neither. It's a quantum field. It behaves like a wave in some conditions and like a particle in others. We were trying to force light into our categories. We were saying, is it an apple or an orange? And nature was saying, it's a fruit. Entanglement is the same. We are trying to say, is it local or non-local? And nature is saying, it's quantum. We have to expand our categories. We have to build new concepts. I think the biggest challenge for the next generation of physicists isn't solving the math. It's not about finding new equations. We have plenty of equations. We have the standard model. We have general relativity. The challenge is conceptual, and it's about building a language that can talk about these things without getting stuck in the old broken metaphors. We need a new way to think about space, time, and matter. We need a way to talk about the world that doesn't depend on our limited macroscopic experience. And that is where you come in. Yet you, the student, you, the curious mind, you have a fresh start. You aren't burdened by the baggage of the last 50 years. You can look at the data with new eyes. You can challenge the assumptions. Don't listen to the experts. Or don't listen to me. Don't listen to the textbooks. Read the textbooks to learn the techniques, to learn the math. But question the interpretation. Ask why. Ask what if. And don't be afraid to look foolish. The most important discoveries come from asking the question that everyone else thinks is too simple or too weird or too stupid. The history of physics is full of people who were told their ideas were crazy. Einstein, Bohr, Heisenberg. They were all considered radicals. They were all fighting against the establishment. So be a radical, be a nuisance, be a pain in the neck, but be honest, follow the evidence, and don't settle for shut up and calculate. Because the goal is not to calculate. The goal is to understand. And if we never fully understand, well, that's okay too. We can still appreciate the beauty of the system, and we can still marvel at the way the universe manages to be both chaotic and orderly, both local and entangled, both simple and complex. That is the true nature of science. It's an adventure. It's an ongoing process. It's not a destination. I want to leave you with this thought. We are part of this system. We are made of atoms, and those atoms are quantum, and they are entangled with the rest of the universe. We are not observers standing outside the universe looking in. We are participants. We are the universe observing itself. And maybe, just maybe, the reason the universe is so weird is because it's trying to tell us something. It's trying to tell us that we are part of a much larger, much more interconnected whole than we ever realized. It's a humbling thought. It makes you feel small, but it also makes you feel connected. You are not a solitary observer. You are a piece of the puzzle. And the puzzle is connected, part to part, from the smallest particle to the farthest star. And that is a beautiful way to think about your place in the cosmos. I have spent my whole life playing with these ideas. I have spent my whole life trying to push the boundaries of what we know, and I'm still here, still curious, still wondering, because that's the best part. The wondering, the not knowing, the feeling that there is always something more to discover. So keep wondering, keep asking, keep looking for the answer, even if you never find it, because the search itself is worth it. Let's think about the future. Quantum computing, quantum cryptography, quantum teleportation. These are the practical applications of entanglement. We are moving from the era of understanding to the era of application. We are learning how to harness these quantum correlations to perform tasks that were impossible before. We are building machines that use entanglement to compute faster, to communicate more securely, to simulate the behavior of molecules. We are becoming masters of the quantum world. And as we do that, as we build these tools, we will learn more about the underlying physics. We will refine our understanding. We will push the boundaries further. It's a cycle. You build a tool, you learn from it. You use what you learn to build a better tool. It's the cycle of science. It's the engine of progress. And we are just at the beginning. We are like the early aviators building gliders, trying to figure out how to fly. We have barely scratched the surface of what's possible with quantum technology. The next 100 years will be incredible. We will see things that we can't even imagine today. We will solve problems that we haven't even identified yet. And it all starts here. It all starts with the question. It all starts with the curiosity. So don't lose that. Protect it, nurture it, because it is the most valuable thing you have. And remember, the world is not the way you think it is. It is much, much stranger. And that is a good thing. I have talked a lot about the math, about the experiments, about the history. But I want to close by talking about the feeling of discovery. That moment when you see something for the first time, when you understand something that was hidden from you before. That rush, that excitement, that joy, that is what it's all about. That is why we do physics. It's not for the prizes. It's not for the fame. It's for that moment, that fleeting, beautiful moment of clarity. And if you can experience that, if you can feel that, then you have succeeded. You have touched the truth. You have connected with the universe in a way that very few people ever get to. So go out there and find your own discoveries. Go out there and ask your own question. Go out there and be curious. Because the universe is waiting for you. The universe is waiting to be understood, and you are the one to do it. I look at the blackboard and I see the chalk dust. I see the equations. I see the math. And I love it. It's beautiful. It's human. It's our best attempt to describe the reality of the situation. It's not perfect. It's not complete. But it's our attempt. And that is enough. We are just trying to read the book of nature. And some chapters are harder than others. Entanglement is one of the hardest. But it's also the most rewarding. It teaches us about the interconnectedness of things. It teaches us about the unity of nature. It teaches us that there is a deep underlying harmony in the universe, even if we don't always see it. So don't get frustrated. Don't give up. Keep looking for the pattern. Keep looking for the harmony. It's there. You just have to look hard enough. And maybe one day you'll be the one to solve it. You'll be the one to write the next chapter. You'll be the one to tell us what it all means. That is my hope for you. That is my challenge to you. Go out there and change the world. Go out there and make your own mark. And remember, the journey is the reward. I've had a good run. I've enjoyed every minute of it. I've chased the mysteries. I've broken the locks. I've played the drums. I've lived a full life. And I've tried to share that with you. I've tried to give you a glimpse of the wonder I felt. I hope I've succeeded. I hope I've sparked something in you. I hope I've made you see the world a little differently, because that is the best I can hope for. I have enjoyed this lecture. I have enjoyed this time with you. It's been a pleasure to share these thoughts, these memories, these questions. And now it's time to go. It's time for you to continue the work. It's time for you to take the torch and carry it forward. The future is yours. The mystery is yours. The universe is yours. Go and explore it. Go and understand it. Go and love it. Because it is a wonderful, strange, beautiful, and mysterious place, and you are lucky to be a part of it. I have no more to say. I have said all I can. The rest is up to you. Thank you for listening. Today's question is the moon still there when you aren't looking at it? Let's get straight to the problem. The year is 1927. The Solvay Conference in Brussels. The greatest minds in the world are gathered in one room. The problem on the table is the new quantum mechanics. Now, to understand the fight, you have to understand exactly what they were fighting over. And to do that, you have to look at how we thought the world worked before 1920. Before quantum mechanics, we had classical physics, Newton, Maxwell. In classical physics, the universe is a machine. If you know where a thing is and you know how fast it's moving, and you know all the forces pushing and pulling on it, you can predict exactly where it will be at any time in the future. It's a clockwork universe, deterministic. If you flip a coin, you might say the result is random, but it isn't really random. It's only random because you are ignorant. You don't know the exact force of your thumb, the air resistance, the exact weight distribution of the coin, the friction of your skin. If you knew all those numbers perfectly, you could calculate exactly whether it lands heads or tail. In classical physics, probabilities are just a measure of our own ignorance. The universe itself knows exactly what it's doing. The coin has a definite state at all time. Then comes the 1920s. Heisenberg, Schrödinger, Born, and Bohr formulate quantum mechanics, and they say something completely different. They say that at the atomic level, an electron doesn't have an exact position and an exact momentum at the same time. It's not that we are too clumsy to measure it, it's that the numbers do not exist in nature. Werner Heisenberg writes down his uncertainty principle. It is an equation. The uncertainty in the position of a particle multiplied by the uncertainty in the momentum of that particle is greater than or equal to Planck's constant divided by 4p. Let us look at exactly what this equation means. The uncertainty in position is the uncertainty in the position of a particle. The uncertainty in momentum is the uncertainty in the momentum of that particle. Momentum is just mass times velocity. Planck's constant divided by 4 pi is a very small number, but it is not zero. The equation says that if you multiply the uncertainty of the position by the uncertainty of the momentum, the result must always be greater than or equal to this constant. This means if you squeeze the electron so you know exactly where it is, making the uncertainty in position very small, its momentum uncertainty must become enormous to keep the product greater than Planck's constant divided by 4 pi. If you measure its speed perfectly, making the uncertainty and momentum zero, it loses its position entirely. The uncertainty in position becomes infinite. It is smeared out across the universe. Max Born looks at Erwin Schrödinger's wave equation and adds the next piece. Schrödinger had found an equation that describes particles as waves, but what is waving? Born says this wave doesn't represent a physical smearing of matter like a water wave. It represents probability. It means before you look, the electron is not in a specific place. It is in a superposition of many possible places. When you make a measurement, the wave function collapses and the electron randomly picks one spot. And this randomness is not classical ignorance, it is fundamental. Nature itself rolls the dice. There are no hidden gears dictating the outcome. Einstein hears this and he hates it. He hates it to his bones. He says God does not play dice with the universe. Einstein is a realist. He believes there is a real objective world out there with definite properties, whether we are looking at it or not. He thinks quantum mechanics works perfectly as a statistical tool. It gives the right answers for large groups of atoms, sure. If you have 1 billion electrons, quantum mechanics tells you exactly how many will hit the left side of a screen and how many will hit the right. But as a complete description of an individual reality? No, Einstein says, you guys are missing something. There must be deeper variables, hidden gears and springs underneath the quantum level that we just can't see yet. You are confusing your mathematical tools with reality. Bohr says, no, Albert. There are no hidden gears. The mathematics is the reality. If you can't measure it, it doesn't have physical meaning. You cannot talk about the trajectory of an electron between measurements. The very concept of trajectory does not exist in nature. So the battle lines are drawn. Solve, 1927. Einstein doesn't just stand up and yell, I disagree. He is a physicist. He operates by physical proofs. He uses thought experiments. And he tries to break Heisenberg's uncertainty principle. If Einstein can prove that you can conceptually know both position and momentum at the same time, then the uncertainty principle is just a measurement problem, a defect of our current instruments, not a fundamental law of nature. And if that happens, Bohr's whole philosophy collapses. Einstein stands up and proposes his first challenge, the single slit experiment. Let's build it in our minds right now. Pay close attention to the mechanics because the devil is entirely in the mechanical details. Imagine a physical screen, a plate of metal with a small vertical slit cut into it. We are firing electrons at this slit one by one. Behind the screen with the slit, there is a photographic plate. When an electron hits the plate, it makes a chemical spot. Now, when an electron goes through the slit, its position in the up and down direction, let's call it the Y direction, is localized by the physical width of the slit. If the slit has a width, then we know the electron's position as it passes through is within that width. The uncertainty in position is approximately that width. Because the slit is narrow, we know the electron's position quite well. But Heisenberg says if you know the position well, the momentum in that direction must become uncertain. The electron gets a kick from interacting with the edges of the slit, and we don't know exactly how much of a kick. As a result, the electrons don't just hit the photographic plate straight on, they spread out. They form a diffraction pattern. Some hit high, some hit low. The narrower we make the slit to know the position better, the more uncertain the momentum becomes, and the wider the pattern spreads out on the plate. Bohr agrees with this. This is standard quantum mechanics. But Einstein says, watch this. Einstein says, let's not bolt the screen with the slit rigidly to the heavy laboratory table. Let's make it mobile. Let's put the screen on frictionless rollers or suspend it from delicate springs so it can move up and down freely. We fire an electron, it goes through the slit and hits the photographic plate. We look at the plate and we see exactly where the electron landed. Now, conservation of momentum is a fundamental law of physics. It applies to everything. If the electron got deflected upwards by going through the slit, it must have kicked the screen downwards, action and reaction. The total momentum of the electron and the screen before the collision was zero in the y direction. Therefore, the total momentum after the collision must also be zero. So, Einstein says, here is what we do to beat Heisenberg. We measure the downward momentum of the screen. After the electron goes through, we look at how fast the screen is moving on its rollers. If the screen got pushed down with a certain momentum, the electron must have gone up with that same momentum in the opposite direction. We measure the screen, so we know the electron's momentum exactly. And we know it went through the slit, so we know its position exactly. We know both position and momentum perfectly. Heisenberg's uncertainty principle is violated. Quantum mechanics is incomplete. Checkmate. The room goes quiet. Everyone looks at Niels Bohr. Bohr realizes the danger instantly. If Einstein is right, the entire foundation of quantum mechanics crumbles. Bohr goes to work. He doesn't retreat to philosophy. He uses physics against physics. He thinks about the physical reality of the setup Einstein just proposed. The next day, Bohr comes back with the answer. And his answer is brilliant because he uses the very rules of the game to trap Einstein. Bohr says, Albert, you want to measure the momentum of the screen. To do that, you have to measure its velocity before and after the electron goes through. But the screen is made of matter. The screen itself is a physical object, which means it must also obey the laws of quantum mechanics. Let's break down exactly what Bohr's counterattack means mechanically. To know the momentum of the screen perfectly, the uncertainty in the screen's momentum must be zero. But if the screen obeys Heisenberg's uncertainty principle, which it must, if quantum mechanics is a universal law of nature, then making the uncertainty in the screen's momentum zero means the uncertainty in the screen's position must become completely infinite. If you set up an apparatus to measure the momentum of the screen perfectly, you must sacrifice all knowledge of exactly where the screen is. If the uncertainty in the screen's position is completely unknown, then you don't know exactly where the slit was when the electron went through it. The physical position of the slit is smeared out. So let's look at the balance sheet. You measured the screen's recoil. Good. You now know the momentum of the electron. But because you measured the screen's momentum, the screen's position became uncertain. And because the screen's position is uncertain, the slit's position is uncertain. Therefore, the position of the electron as it passed through the slit is now exactly as uncertain as Heisenberg demanded. When Bohr does the rigorous math on the chalkboard, he shows that the uncertainty in the slit's position exactly restores Heisenberg's relationship for the electron. The product of the uncertainties in position and momentum still equals Planck's constant divided by 4 pi. You see exactly what Bohr did? He didn't introduce new magic. He just refused to let Einstein treat the measuring instrument classically. Einstein tried to step outside the quantum universe to measure it. Bohr pulled him back in and said, no, the ruler you use to measure the quantum world is also quantum. The scale you use to weigh the quantum world is also quantum. Einstein was defeated on this point. He saw the logic, but he wasn't. Solvay 1927 continued, and Einstein came up with a modification, the double slit. Einstein says, fine, let's use 2 slits. We know that if you fire electrons at a screen with 2 slits, they form an interference pattern on the plate behind them. Bands of high electron strikes and bands of 0 electron strikes. This pattern only happens if the electron goes through both slits at the same time and interferes with itself as a wave. But an electron is a particle. It hits the screen in one spot. Einstein says it must go through one slit or the other. If we can determine which slit it goes through and still get the interference pattern, we prove the electron has a definite trajectory, a particle property, while acting like a wave. So, Einstein modifies the experiment. Let's put a detector on the first slit. Maybe the first slit is on a very sensitive spring. If the electron goes through the top slit gets a tiny kick of momentum. If it goes through the bottom slit gets a kick. We read the momentum of the slit to see which path the electron took. Bohr steps up again. He applies the exact same mechanical logic. He says to read the momentum of the slit to know which way the electron went, you must measure its momentum with a certain accuracy. But by doing so, you introduce an uncertainty in the slit's position. Now, the interference pattern on the back wall depends entirely on the exact distance between the 2 slits. The waves from the top slit and the bottom slit must arrive in phase to add up or out of phase to cancel out. If you make the position of the top slit uncertain to measure its momentum, you shift the phase of the wave coming out of it. The wave from the top slit is now jiggling back and forth randomly compared to the wave from the bottom slit. Bohr calculates the exact amount of jiggling. He proves that the uncertainty in the slit's position shifts the waves just enough to completely wash out the interference pattern. If you measure which way the electron goes, you destroy the interference. You get a boring classical spread of particles. You can have the wave or you can have the particle trajectory. You cannot physically have both at the same time. The mechanics of the universe forbid it. Einstein packs his bags. 1927 goes to Bohr, but Einstein retreats, regrouped, and realized his mistake. He realized he couldn't use position and momentum. The physical interplay of spatial measurements was too tight. Bohr would always use the position, momentum, uncertainty of the measuring device to block him. Einstein needed to find a different pair of variables. He needed to step out of space and into something Bohr couldn't manipulate with physical springs and rollers. He needed energy and time. 3 years pass. 1930, the Sixth Solvay Conference in Brussels. The debate resumes, and this time, Einstein brings a weapon so perfectly designed, so mathematically devious, and so structurally flawless that it nearly breaks Niels Bohr's mind. This is the famous photon box experiment. I want you to picture this mechanism in your head with absolute clarity. We are going to build Einstein's machine right now. Einstein says, forget slits, forget electrons bouncing off screens, and let's talk about light and mass. Let's use my own equation, the one nobody disputes, energy equals mass times the speed of light squared. Here is the machine Einstein draws on the board. We have a box, a physical box. Inside the box, there is a gas photon, light bouncing around. The walls of the box are perfect, ideal mirrors. Absolutely no light can escape. On the side of the box, there is a small hole. Covering the hole is a mechanical shutter. The shutter is connected to a highly precise clockwork mechanism inside the box. We can set this clock. We set it to open the shutter at an exact predetermined time. Let it stay open for an incredibly short fraction of a second, and then snap shut. Let's say we set the clock to open the shutter at exactly 12 o'clock. The shutter opens, a single photon of light escapes the box, and the shutter immediately closes. Now, how do we break the uncertainty principle with this? Heisenberg has a second uncertainty relation, not just position and momentum. He has one for energy and time. It is written, the uncertainty in energy multiplied by the uncertainty in time is greater than or equal to Planck's constant divided by 4 pi. It means you cannot know the exact energy of a quantum event and the exact time that event happens simultaneously. If you know the exact time a particle is emitted, you cannot know its exact energy. Einstein says we can. Watch the mechanics carefully. Before the experiment begins, we weigh the entire box. We hang it from a precise spring scale and measure its mass perfectly. We record the mass, let's call it the first mass. Now we wait. The clock ticks. At exactly 12 o'clock, the shutter opens. A photon escaped. The shutter closes. Because the clock is a precise mechanical instrument inside the box, we know the exact time the photon left. The uncertainty in time is practically zero. After the photon leaves, we weigh the box again. The box has lost a single photon. Now, photons have energy. And according to my own theory of special relativity, energy has an equivalent mass. Energy equals mass times the speed of light squared. Because energy left the box must be slightly lighter. We read the new mass on the scale, the second mass. We subtract the two masses. The first mass minus the second mass equals the change in mass. We now know exactly how much mass was lost. We take that mass difference and multiply it by the speed of light squared. The change in energy equals the change in mass times the speed of light squared. We now know exactly how much energy the escaping photon had. The uncertainty in energy is practically zero. We know the exact time the photon left. We know the exact energy of the photon. The uncertainty in energy times the uncertainty in time equals zero. Heisenberg is wrong. The uncertainty principle is not fundamental. Quantum mechanics is incomplete. When Einstein presented this at the 1930 Solvay conference, the room was paralyzed. The logic was airtight. It was entirely mechanical. Weigh a box, check a clock, use relativity. Where is the flaw? Leon Rosenfeld, a brilliant physicist who was there, described Niels Bohr's reaction. Bohr was completely devastated. He was walking around the conference hall, going from person to person, his face pale, muttering, "It cannot be true. If Einstein is right, it is the end of physics." Bohr couldn't find the flaw. He stayed up the entire night. He did not sleep a wink. He sat in his room, sweating, calculating, drawing diagrams, desperate. He knew in his bones that Einstein had to be wrong, but he couldn't see where the physics broke down. Morning comes. The physicists gather for breakfast. Einstein has a quiet, victorious smile on his face. Bohr walks into the conference room. He looks exhausted, but he has a smile on his face, too. He goes to the chalkboard and he draws Einstein's box. But Bohr doesn't just draw a simple square with a clock. He draws the box in meticulous, excruciating mechanical detail. He draws the heavy iron stand holding the box. He draws the suspension spring from which the box hangs. He draws a pointer attached to the side of the box. He draws a vertical ruler and a scale bolted to the iron stand used to read the position of the pointer to determine the weight. He draws a small weight hanging from the bottom of the box that we use to calibrate the pointer to the 0 mark. Bohr turns to the room and says, "Albert, you've forgotten how to weigh things." But let us look at the actual physical mechanics of weighing this box. To weigh the box, you must read the position of the pointer against the scale on the stand. But the box is a physical object. If we are to read its weight with high precision, we must determine its vertical position. Let's call it a coordinate. And we must ensure its vertical momentum is 0, so the pointer is steady. But the box is subject to the uncertainty principle. The uncertainty in its position times the uncertainty in its momentum is greater than or equal to Planck's constant divided by 4 pi. If we want to measure the mass perfectly, we must constrain the momentum uncertainty. That means there must be an uncertainty in the position of the box on the spring. The box is jiggling quantum mechanically on the spring. Einstein says, so what? Why does the box jiggling matter? The clock is inside the box. Here is where Bohr delivers the killing blow, and it is the most beautiful poetic justice in the entire history of science. Bohr uses Einstein's own greatest creation, general relativity, to defeat him. Bohr says, "Albert, in 1915, you taught us that gravity affects the flow of time. A clock higher up in a gravitational field ticks faster than a clock lower down. Time runs slower near a massive body. Because the box is hanging from a spring and because it has a quantum uncertainty in its vertical position, the clock inside the box is sitting in an uncertain gravitational potential. We don't know exactly how high the clock is in the Earth's gravitational field. Because we don't know its exact height, we don't know the exact rate at which it is ticking. The uncertainty in the position of the box creates a fundamental uncertainty in the ticking rate of the clock inside the box. Bohr goes to the board and does the math. It is brutal and precise. First, he links the uncertainty of the momentum to the uncertainty in the mass measurement, taking into account the time it takes to make the weighing. A force is a change in momentum over time. So the uncertainty in the gravitational force is the uncertainty in momentum divided by time. But gravitational force is also mass times gravity, so the uncertainty in momentum divided by time equals the uncertainty in mass times gravity. Second, he uses Einstein's time dilation formula from general relativity. The change in the clock's time rate depends on the height change, the strength of gravity, and the speed of light. The formula is the uncertainty in time divided by the time of measurement equals gravity times the uncertainty in position divided by the speed of light squared. Bohr multiplies these physical relationships together. He takes the position momentum uncertainty of the box, which is the uncertainty in position, times the uncertainty in momentum is greater than or equal to Planck's constant, and substitutes the terms he just derived from gravity and mass. When Bohr finishes the algebra, the result on the board is inevitable. The gravity cancels out, the time of measurement cancels out the uncertainty in the energy, which is the uncertainty in mass times the speed of light squared multiplied by the uncertainty in the time caused by the gravitational jiggling, equals exactly Planck's constant. The uncertainty in energy times the uncertainty in time is greater than or equal to Planck's constant. Heisenberg holds, quantum mechanics is saved, Einstein is hoisted by his own petard. It was a staggering victory for Niels Bohr. Einstein was astonished. He looked at the board, looked at his own theory of relativity being used to defend the quantum mechanics he despised, and he had to admit the logic was flawless. He conceded the point. You cannot mechanically violate the uncertainty principle. The mathematics of quantum mechanics is internally, rigidly consistent. Every time you try to build a machine to break it, the machine itself obeys quantum rules that hide the information from you. But if you think Einstein gave up, you don't know Einstein. Einstein never gave up. He just changed his strategy. He realized he could not prove quantum mechanics was logically inconsistent. Bohr would always win the mechanical street fights. So Einstein decided to prove it was physically absurd. He decided to show that if quantum mechanics was the final complete truth of reality, then the universe must operate by rules so utterly nonsensical, so completely disconnected from any reasonable definition of physics, that no sane physicist could accept it. 5 years pass. It is 1935. Einstein is now at the Institute for Advanced Study in Princeton, having fled Europe. He works with two younger physicists, Boris Podolsky and Nathan Rosen. Together, they publish a 4-page paper. It is simply titled, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" It becomes known as the EPR paradox. It is the most downloaded, most cited, most fiercely debated paper in the history of quantum physics. This paper shifts the battlefield entirely. We are no longer talking about boxes and springs and slits. We are talking about something much deeper. We are talking about the fundamental nature of information. We are talking about entanglement. Listen carefully to the EPR argument because it is incredibly subtle, entirely devoid of physical springs, and incredibly dangerous. Einstein, Podolsky, and Rosen start with a definition. They know Bohr will attack their terms, so they carefully define what reality means in a physical sense. They write, if without in any way disturbing a system, we can predict with certainty, that is, with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. What does that mean in plain English? It means if I can know exactly where something is without looking at it, without shining a light on it, without touching it, or interacting with it in any way whatsoever, then that thing must have actually been there all along. Its position is real. It is an objective fact of the universe independent of my observation. And the moon is there even when I don't look, because I can predict its position based on the tides without looking at the sky. Now, let's construct the EPR thought experiment based on this definition. Imagine a single particle. It is sitting completely still at the exact origin of our coordinate system. Its total momentum is exactly zero. Suddenly, this particle decays. It splits into two identical particles. Let's call them particle A and particle B. Particle A shoots off to the left and particle B shoots off to the right. Because of the fundamental law of conservation of momentum, the total momentum of the universe must remain zero. Therefore, whatever momentum particle A has, particle B must have the exact opposite. If A has a momentum of minus 10 units, B must have a momentum of plus 10 units. Furthermore, because they started at the origin at the same time and travel at the same speed, if particle A is at position minus 5 meters from the center, B must be at position plus 5 meters from the center. Their properties are perfectly mathematically correlated. In modern terms, Schrödinger coined a word for this. They are entangled. Their mathematical wave function is not two separate equations. It is one single equation describing the joint state of both. Now, we let these particles fly apart. We let them travel for a long time. We let them travel so far apart that particle A is sitting in a laboratory on Earth and particle B is sitting on a planet orbiting Alpha Centauri 4 light years away. Einstein says, let us now make a choice. We are the experimenter on Earth, sitting with particle A in our machine. Choice 1, we decide to measure the momentum of particle A. We build a momentum measuring device, we let A hit it, and we measure it precisely. Let's say we find it has a momentum of minus 10. Instantly, without doing any work, without waiting for a signal, we know with absolutely 100% certainty that the momentum of particle B on Alpha Centauri is plus 10. Now, apply Einstein's definition of reality, because we can predict the momentum of particle B with absolute certainty without disturbing particle B in any way. It is 4 light years away, and nothing we do to A can physically reach B instantly without breaking the absolute speed limit of the universe, the speed of light. Particle B must possess a definite momentum as an element of physical reality. The momentum of B was already a real fixed number sitting there on Alpha Centauri before we even pushed the button to measure A. Choice 2, instead of measuring momentum, we reset the universe and decide to make a different choice. We decide to measure the position of particle A. We put up a screen, we measure it, and we find it is exactly at position X. Because the particles flew apart symmetrically from the origin, we instantly know with 100% certainty that particle B is exactly at position minus X. Again, by Einstein's definition, because we can predict the position of B without sending any physical signal to disturb it, particle B must possess a definite position as an element of physical reality. Here is the trap. The jaws close. Einstein says the measurement I make on particle A cannot possibly affect particle B physically. They are separated by a gulf of space. To say that my choice of turning a dial on Earth physically changes the state of a particle 4 light years away instantly requires what Einstein calls spukhafte Fernwirkung, spooky action at a distance. It would require a magical telepathic signal traveling infinitely fast across the void, violating the core law of relativity. We assume there is no spooky action. Local realism must hold. Things are only affected by their immediate local surrounding. Therefore, since I could have chosen to find the exact momentum of B, and I could have chosen to find the exact position of B without touching B at all, then particle B must have possessed both a definite position and a definite momentum all along simultaneously. The information was already packed inside the particle when it left the origin. But Heisenberg's uncertainty principle says a particle cannot possess both a definite position and a definite momentum simultaneously. The quantum mechanical wave function simply does not have the mathematical room to contain both numbers. The conclusion? The checkmate? Einstein says quantum mechanics is right about the correlation, but it is incomplete. The wave function does not describe the full physical reality of the particle. The particle has hidden properties, secret variables, tiny little instruction manuals packed inside it when it was born that tell it exactly where it is and how fast it's going. Quantum mechanics only gives us a statistical blur because it is a primitive, incomplete theory. It is missing the deeper gears of the universe. This paper hits the physics community like a meteor. It is utterly profound. Einstein has conceded that uncertainty holds for our clumsy measurements, but he has logically, rigorously shown that reality itself must possess definite properties underneath the uncertainty unless you are willing to accept telepathic, instantaneous communication across the universe. And no physicist in 1935 was willing to accept magic. Niels Bohr is in Copenhagen when he reads the EPR paper. His colleague Leon Rodenfeld describes the scene again. Bohr drops everything. All other research stops. He realizes Einstein has just struck a dagger at the very heart of the Copenhagen interpretation. Bohr cannot use a spring or a clock to get out of this one. Einstein's used pure logic and locality. Bohr's response to the EPR paper takes months to write. When he finally publishes it, it is notoriously difficult to read. It is dense, heavily philosophical, and lacks the crisp mathematical checkmate of the 1930 photon box. But if you strip away the heavy, convoluted language, Bohr's argument is radical. It is the exact moment that physics totally severs its ties with classical human common sense. Bohr writes a reply. He attacks Einstein's fundamental premise. He attacks the phrase, without in any way disturbing a system. Bohr says, Albert, you think that because particle B is 4 light years away, measuring particle A does not disturb particle B. You're thinking of them as two separate, isolated objects. But they are not. They were born from the exact same event. They share a single mathematical quantum state. They are one indivisible system. Bohr argues that the very concept of physical reality cannot be applied to a property like momentum or position until an actual physical experimental arrangement is set up to measure it. Before you measure particle A, it is completely meaningless to talk about the definite momentum of particle B. When you make the choice on Earth to measure the momentum of A, the entire experimental setup across the entire universe becomes a momentum measuring apparatus for the whole entangled system. A plus B. You haven't sent a physical force across space to push or pull B. Einstein is right that there is no mechanical signal. Instead, the very definition of what is real for B is inexorably, fundamentally tied to the measurement context you established at A. Bohr is saying that reality is contextual. There is no independent, objective reality to a particle's properties outside of the act of measurement. You cannot ask what particle B is doing when you aren't looking at it, even if you are looking at its twin, because until the measurement is completed, particle B's momentum is not a physical concept that the universe recognizes. Let's translate this into cold, hard logic. Einstein says reality is local. The things are only affected by their immediate surrounding. And real, things have definite properties before you look. Bohr says quantum mechanics forces us to abandon either locality or realism. Bohr essentially says, I don't care if it looks spooky to you, Albert. That is how nature actually works. The entanglement is real. The particles are not separate entities until the measurement breaks the entanglement and forces them to choose a state. Einstein reads Bohr's reply and basically rolls his eyes. He thinks Bohr is hiding behind semantic trickery. He thinks Bohr is practicing mysticism, not physics. Bohr reads Einstein and thinks Einstein is stubbornly stuck in the 19th century, refusing to accept the new reality the mathematics demand. The debate between them essentially ended there. The lines were drawn in concrete. Einstein died in 1955, working on his unified field theory, still believing quantum mechanics was a temporary illusion, a mathematical stopgap until a real deterministic local theory was found. Bohr died in 1962, believing to his last breath that he had successfully defended the quantum revolution and that nature was fundamentally statistical. For 30 years, from 1935 to 1964, physicists ignored the debate. They thought it was just a philosophical argument between two old men. Who cares? The working physicists said. The equations work. We can build lasers. We can build transistors. We can split the atom. Shut up and calculate whether the particle has a definite state before measurement or whether it is spooky action at a distance doesn't change a single number on our dial. It's metaphysics. It's unprovable. But physics is not philosophy. Physics demands physical proof. Physics demands an experiment. In 1964, an Irish physicist named John Stuart Bell was working at CERN. He was thinking about Einstein's hidden variables. He looked at the EPR paper and he did something absolutely impossible. He found a way to test it. Bell realized that you don't just have to measure exact position or exact momentum. You can measure the spin of the entangled particles along different random angles. Particle A goes left, particle B goes right. I measure A's spin on the vertical axis. You measure B's spin on an axis tilted 45 degrees. Bill did the math. He proved mathematically that if Einstein was right, if there were hidden gears and springs inside the particles, if local realism was true, and the particles had instruction manuals written before they separated, there was a strict, hard mathematical limit to how correlated the measurements of particle A and particle B could be over many trials. He wrote down an inequality. It is known today as Bell's inequality. It is a simple statistical boundary. It says if the universe is local and real, the correlation between A and B must be less than or equal to a certain number. If you do the experiment and the correlations obey Bell's inequality, Einstein is right. The universe is local. The universe is real. The moon is there when you aren't looking. Quantum mechanics is an incomplete theory, hiding deeper mechanisms. If you do the experiment and the correlations violate Bell's inequality, if the particles are more perfectly correlated than local hidden variables allow, Bohr is right. The universe is deeply, fundamentally, terrifyingly weird. Either properties literally do not exist before measurement, or spooky action at a distance is a real, instantaneous physical fact of the cosmos. In the 1970s, John Clauser built the first machine in a basement in Berkeley. In the 1980s, Alain Aspect built a better machine in Paris, switching the measurement angles while the particles were in flight, moving at the speed of light to ensure no signal could possibly travel between them. And all the way up to recent years, physicists have built larger and larger machines. They created entangled photons, they sent them down fiber optic cables. They sent them to satellites in orbit. They measured them. They tallied up the spins. They checked the correlation. They put nature to the ultimate test. And they found the results. The data is in. But I'm not going to tell you what they found. Not quite yet. Because before you know the final answer, before you know who won the war, you need to sit in the quiet and ask yourself what you truly believe about the universe you live in. Think about the physical implications of what we have just talked about. If Einstein is wrong, and you measure an electron in a lab on Earth, and it instantly, magically determines the state of an electron across the galaxy, what does that mean for the space between us? What does that mean for the concept of distance? Are we all just local manifestations of a single, indivisible, cosmic web where space is an illusion? If the universe decides the outcome of a measurement only at the exact fraction of a millisecond that your eye registers the photon, what was the universe actually doing a second before? Is reality just a rendering engine that only paints the pixels when you turn your head to look? We have dissected the pure mechanics of the debate. You have seen the metal slits, the bouncing screens, the photon boxes, the clock gears, the gravity wells, and the entangled pair. You have seen the two greatest minds in human history push the absolute limits of human logic to the breaking point. But nature doesn't care about human logic. Nature does what it wants. Nature has the final say. The experiments have been done. The statistics have been compiled. The Nobel Prizes have been awarded. The final verdict between Albert Einstein and Niels Bohr has been written by the universe itself in the cold, hard data of Bell's inequality. And the truth of what is actually happening in the dark when you aren't looking is far more terrifying, far more alien, and far more beautiful than either Einstein or Bohr could have ever imagined.